necessary.
Great. I'll make that. Already started. Yeah.
All right. Well, have a good meeting, and before I leave, I'll just type my name and email in the chat in case you need me. You can email me. I should be here fairly promptly.
Sure. Thank you, Steve.
Thank you very much.
All right. Hello, everyone. My name is Ziran Wang, and I think we're right on time. We can start our workshop. And this will be the second workshop on Internet of Things in Intelligent Transportation Systems, which we held our first workshop last year during IV. And this will be an online workshop for sure, but I guess maybe some of you might be in Indianapolis right now attending ITSC in person. But we'll conduct our workshop, all these talks through Zoom. And this is going to be a 4-hour session. We have 7 speakers lining up, very distinguished professors and researchers across industry and academia. And I'm showing our website of this workshop. And as I scroll down, you can see, the topics of this workshop is focused on all different elements of IoT, and more specifically about things like digital twin, VCPS, cybersecurity, vehicle to cloud, AI and big data for sure, edge computing, modeling and simulation for traffic, and connected and automated vehicles, things like that. And as I said, we have 7 speakers, including Professor Alfred Chen from UC Irvine, Professor Sharon Di from Columbia University, Dr. Changyi Luo from Toyota Motor Corporation, Japan, Professor Chen Liu from Nanyang Technological University, Professor Andreas Markopoulos from University of Delaware, Professor Huizongshi from Wayne State University, and Professor Xuesheng Zhou from Arizona State University. So all those talks, I promise, will be very exciting and cover a lot of different angles of IoT. And this is the agenda of this workshop. First will be Professor Liu, and then Professor Huizongshi, Professor Markopoulos, Professor Chen, Professor Di, Dr. Luo, and lastly but not least, Professor Zhou. And another round of welcome from all our workshop organizers, including myself from Toyota Motor North America, Professor Qi Zhu from Northwestern University here in the United States, Dr. Guoyan Wu from UC Riverside, Professor Jiaqi Ma from UCLA, Professor Changwei Lin from National Taiwan University, and Dr. Bowen Zheng from Pony.ai. And just FYI, this workshop is actually one of our ongoing activities of our technical committee, which is clicking into our technical committee website, which will be the same name, right? Technical Committee on IoT in ITS. This is one of the 10 technical committees of IEEE ITSS. And you can actually find last year's IoT and ITS workshop here in this website, and the recordings. And we have actually some announcements. We have one special issue going on in the Transportation Research Part D, which I will spread the words later in our newsletter. And we'll have another one which is specifically working on IoT and ITS, which we're working on this call for proposal right now, and hopefully that will be released soon in IEEE Transaction on Intelligent Vehicles. And this is the second IoT and ITS workshop. It's a fourth workshop of our technical committee, 2 on ITSC and 2 on IV. And our committee, which will be the same as this workshop ongoing, will be focused on different angles of IoT, digital twin edge computing, cybersecurity, smart cities, parallel driving, parallel intelligence, vehicle cyber-physical systems, and so on and so forth. And actually, a lot of the speakers today, they are from our committee as well. You can identify some of the names right here, like Dr. Lu, Professor Huizongshi, and Professor Xuesong Zhou. So they're also from our committee, and they will give very exciting talks today. So without further ado, let me introduce our first presenter, which will be Professor Chen Lu. And actually, he has a pre-recording video right here, which I will play in a minute. And it will be the only one because Professor Lu has some other arrangements during this day, so he cannot join us in person, and he will be the only one conduct the presentation through pre-recorded video. And let me put this right here. So Professor Chen Lu is an Nanyang Assistant Professor of School of Mechanical and Aerospace Engineering with a joint appointment in School of Electrical and Electronic Engineering and the Cluster Director in Future Mobility Solutions at ERI Aten, Nanyang Technological University in Singapore. He received his bachelor's degree in automotive engineering, Wuhan University of Technology in China in 2010, and a PhD degree at Department of Automotive Engineering in Tsinghua University in China in 2016. He was a joint PhD researcher at EECS Department, University of California, Berkeley, during 2014 to 2015, and worked as a research fellow at Advanced Vehicular Engineering Center in Cranfield University in the UK during 2016 to 2018. He joined NTU and founded this research lab, which we'll talk about in a minute, in 2018, and his research focuses on advanced vehicle control and intelligence, where he has contributed 2 books, 2 book chapters, over 100 papers, and obtained 12 granted patents and 1 technology disclosure. So here is his presentation.
Hello everyone, my name is Lu Chen from Nanyang Technological University, Singapore. Thank you very much for the kind invitation. It is my great honor to join this special session at ITSC and share the recent research progress in my group. So today, the topic of my talk will be human-like autonomous driving and human-machine systems. First, let me briefly introduce myself, and my own research team. I joined NTU in 2018 and founded my own research lab. I name it AutoMan. As you can see, there are 2 keywords, auto and man. So basically, we're working around automated driving and human-machine systems. The main research topics include human-like autonomous driving, human-machine collaboration, human-in-the-loop AI, and intelligent electric vehicle. So far, we have developed some of the testing facilities to support our research, including this human-in-the-loop driving simulator, a downscaled autonomous mobile robot, a 1-seater autonomous testing vehicle. And here in NTU, we have our own autonomous vehicle testing center on campus. It is the first one and also the only one AV testing track in Singapore and Southeast Asia. And today I would like to share with you two major research directions in my group: human-like autonomous driving and human-machine systems. The first topic is human-like autonomous driving. Here the idea is not to only realize those basic functionalities of autonomous driving. Instead, we hope to move one step further, to further improve the smartness and ability of AV systems, making their decision-making, path planning, and control more like human drivers. Because for our human drivers, we have different driving styles or different habits and preferences on driving. Some drivers are aggressive and some are more conservative. And for different travel demands, their corresponding driving behaviors could be quite different. So in the future, we hope our AVs could be smart enough. They could have their own human-like characters and driving styles, and they could adapt to different travel demands of individual users. In order to realize human-like autonomous driving, first we need to understand our human driver behavior and mechanisms. How does a human driver drive a car? Here we use inverse reinforcement learning to model human driving behavior. More specifically, first we formulate our human driving behavior with different objectives and preferences as a multi-objective optimization problem, and design reward function to represent it. And then by leveraging inverse reinforcement learning and naturalistic driving data, the model can learn the parameters of the reward function directly from the real-world driving data. Here are the results of the developed inverse reinforcement learning model. We use the model-generated trajectory to compare to the ground truth, which is the real-world trajectory data, to evaluate the human likeness, or let's say the closeness to human trajectories. From this visualized trajectory diagram, we can find that the inverse RL model can accurately generate a trajectory which is very close to the ground truth. In addition, compared to the other existing models, including the constant velocity model, IDM, and mobile model, the proposed method shows a significant improvement in terms of trajectory's human likeness. Besides, driving style is another key feature which can represent different human driving behaviors. As we mentioned before, some drivers are aggressive and some are more conservative, caring more about safety. Here we first classify our typical driving styles into three categories: aggressive, moderate, and conservative, and use Lstm neural network to construct their correlations to vehicle dynamic states, including velocity, acceleration, jerk, in both longitudinal and lateral directions. And then the model is trained by using the real-world driving data. Eventually, the well-trained Lstm model is able to accurately identify different driving styles. Beyond this, scene understanding, prediction, and decision-making are also very important for constructing human-like autonomous driving. Here, one of our current main focus is interaction-aware trajectory prediction. The task is very challenging but very important for AVs. Because for our human drivers, when we drive a car on road, we're not driving alone. Around us, there are many other road users: passenger cars, truck, lorries, buses, cyclists, motorcycle, pedestrians, and etc. And when we drive, we need to make decisions based on the current traffic situation and our surrounding vehicles' actions. Our ego car's behavior will affect others' action, and others' driving behaviors will also impose impacts on our decision making and control. So we can see that there are complex interactions between traffic participants in real-world driving. So in order to further improve the smartness of AV and allow them to understand current situation and even further forecast the future complex interactions between vehicles, here we develop an integrated Lstm CNN model to predict a single vehicle's trajectory. Here we use Lstm encoders to first extract features from the historical trajectory data of each vehicle, and then put them into CNN model to extract the interaction information. Next, combine the output of this CNN model together with the sequential feature of the ego car, and then the predicted trajectory can be generated through the Lstm decoder. This is the prediction for a single car. Based on the previous framework and model, we further expand the interaction-aware prediction from single vehicle to multiple vehicles. In this method, we leverage graph neural network to model the interactive features among all focused vehicles and extract their interaction features. Finally, the trajectories of all focused vehicles can be generated simultaneously. With this method, we participated in 2 major AV prediction competitions. Last year, we won the winner of the Interact Challenge, which was organized by Berkeley MSc Lab in NeuroIPS. And this year, we won the first place in the interaction prediction track in Waymo AV competition held in CVPR. Here are some of the visualized results of the interaction predictions. You can see that the interactions include multiple heterogeneous agents, vehicles, pedestrians, cyclists. But actually, trajectory prediction is not the final goal. The predicted outcome should be able to benefit the downstream decision making and control. This is our real target, to further improve the safety and smartness of our AVs in their decision making and controls. So here, based on previously developed driving style identification model and the interaction aware prediction module, we utilize game theory to further model human interactive decision making process, formulated as a multi-objective optimization problem. In this way, the human-like features are expected to be represented in the decision-making output. So far, we have applied our human-like decision-making algorithms in simulations under various driving conditions, including the overtaking scenario on multi-lane highway, multi-lane roundabout, and intersections in urban, to validate their feasibility and effectiveness. Recently, we are also looking into integrate and test them on an electric AV bus, real AV bus in the AV center on our campus, to test its performance in real-world conditions. Okay, this is the topic 1, human-like autonomous driving. Well, the second main direction in my lab is human-machine collaboration for automated driving. As we know, the ultimate goal of AV development is fully autonomous, level 5, based on SAE's 6-level definition. However, due to the current limitations in the smartness of AI, AVs are still unable to handle all kinds of situations, especially in those highly complicated urban scenarios and some emergency conditions. So we believe that before realizing full autonomy in all conditions, human drivers are still needed. They should be still within the control loop to ensure the safety and stability of our vehicles. Because our humans exhibit strong robustness and adaptability towards scene understanding. So we are able to make fast decisions in emergency and complex conditions. However, challenges are still remain. For human beings, our behaviors are easily affected by physical and physiological factors. Our cognitive states like attention, intention, workload are usually invisible and can hardly be measured directly by using sensors. In addition, because our humans are not physical actuators, we cannot directly control a human to do this or that. We can only provide warning or provide guidance when their behaviors are not ideal. So all these facts pose new challenges in human-machine collaborations in AV. Here we develop a novel human-machine collaboration framework. We have no assumption on human driver performance is always better than automation or automation is better than human. Instead, we need to monitor both human and machine status and assess their performance simultaneously. In the middle layer, based on their performance assessment, we have an additional module to evaluate the risk and adaptively allocate the entire control authority to human and machine. In the meantime, we provide multi-modal interface, including visual, audio, haptic signals to guide and assist human-machine interactions to make sure the overall human-machine system to be safe and efficient. In order to realize the high-level human-machine collaboration framework, we made effort to develop multiple supporting subsystems. So here, first we use computer vision techniques to first understand human driver in-cabin activities, to understand what they are doing in the cabin. Here we develop our models using deep learning and transfer learning. Further, from these visible activities, we need to understand drivers' invisible cognitive states. Here, based on drivers' facial expressions and detected upper body movement, fingers, wrist, arm, shoulder movement, and then we can further analyze driver's cognitive attention, whether his or her attention is on driving. Besides, still based on computer vision technology, we combine driver's eye gaze direction and scene features to further improve the attention estimation accuracy. Here we use RGBD camera to first capture driver's eye gaze direction to understand where the driver is looking at. In the meantime, we use saliency map, which is obtained from the scene analysis of surrounding environment to infer potential attentional region of the driver, and then link them up and fuse them together to further improve the estimation of driver's attention level. In addition to attention, intention is also very important state for human-machine interaction, because we need to understand human driver's intent in order to support him or her and mitigate any conflicts happening between human and machine. Although the intention itself cannot be directly detected, it can be reflected indirectly by certain patterns of driver activities. For example, if a driver wants to change a lane and overtake a car, first he will need to check mirrors and give a steering light and then take steering actions on the steering wheel. So here we develop a deep neural network model and analyze the driver activity patterns, and then extract the intention from the pattern features of drivers' sequential actions. In addition to cognitive states, modeling and monitoring driver physical states are also very important. Here we focus on the neuromuscular dynamic state, because during driving, it is our arm generating force and applying torque on the steering wheel. So it is very important to monitor driver's muscle state in order to achieve a safe and smooth driver automation interaction or transition. In lab, theoretically, we can attach EEG sensors on our subject's body. However, in real-world driving, it would be very annoying if we ask drivers to wear a lot of sensors on body or to wear a lot of hardwares. So here we first model the steering wheel arm interaction system by using a simplified mass spring model. Meanwhile, we did driver in the loop experiments and collected a lot of naturalistic driving data with multiple driving postures. Then we did system identification using the data to identify key parameters of the model. Finally, we found that the stiffness coefficient is highly correlated to the neuromuscular dynamics. So in future, in real-world applications, we can leverage this stiffness coefficient to infer driver muscle state, and it is because it is easy to measure online by using steering torque and angle. Apart from driver state estimation and monitoring, we also design adaptive shared control for ensuring safety of AV. By evaluating the performance and risks of both human driver and automation systems' intention and actions, the shared control module will dynamically allocate control authority to human and automation. And the haptic steering torque will be generated to better provide guidance and assistance to human driver during shared control and takeover. Finally, by integrating all subsystems together, we develop our first version human-machine collaboration prototype system and implement it on the real testing vehicle. Experiments have been conducted under typical driving conditions. Okay, that's all for my presentation today. Thank you very much for your attention. And if you are interested in our research, or if you have any queries regarding our research, please feel free to draw me an email. I'd be very happy to discuss with you. And I look forward to meeting you in the future in person.
All right, so I think that's it from Professor Lee. And as I said earlier, he has some other arrangements, so he cannot join us in person. So if you have any question, please feel free to shoot him an email with this email address right here. And also for all those different sessions during this workshop, we have already been recorded, and we will upload that to our workshop website as soon as the workshop has been finished today. So you can always trace back, and if you have any question, just feel free to contact him. So our next presenter, let me stop share, will be Professor Huizongshi. And Professor Shi, you can start share your screen. And Dr. Shi is a Charles H. Gershenson Distinguished Faculty Fellow and a Professor of Computer Science with Wayne State University in the United States, where he directs the Mobile and Internet Systems Laboratory and Connected and Automated Driving Laboratory, investigating performance, reliability, power, and energy efficiency trust and privacy issues of network computer systems and applications. He's one of the world leaders in the edge computing research community and published the first book on edge computing. His paper entitled Edge Computing, Vision and Challenges has been cited more than 2,900 times. He's an IEEE fellow and an ACM distinguished scientist. Okay, Professor Shi, you can start your presentation.
Thank you, Ziran. Can you hear me?
Yes, very clear.
Good, good, good. You have a very nice background. Is that Pittsburgh?
No, that's actually my hometown, China, Chongqing, China.
Oh, I've been there before, so I feel like, okay, good. Well, thank you very much for having me here. It's a great pleasure. I noticed that, we have a list of very nice talks here, but unfortunately we have to be like this way online.
Yeah.
Hopefully next year we can meet, those topics are very interesting. So my talk will be a little bit on high level, so that, trying to give you guys some idea, something that I think about, in the last few years, has been working in the connected autonomous driving, and then also IoT. So I'm thinking about, what's the next thing? So that was basically is what I want to share with you today. So here is, what are we going to cover for the next, 20 some minutes. So I want to say, starting with why vehicle computing is here. You might wondering that, vehicle has always been there. So, but I view that there are something new is going to happen. And then in order to support this kind of vehicle computing, and then we will talk a little bit about edge intelligence, in particular, edge computing running on the vehicle with AI and etc. Like a previous talk, Dr. Liu mentioned that their work is very interesting, but that's, to implement that, you have a lot of machine learning and this stuff is going to be running on the vehicle. And finally, I wanted to share a little bit about, in the CAV space, some of our previous work and some of the ongoing work here. So I want to start with this figure, which was, I wrote a viewpoint published on the IEEE Internet Computing magazine in May, June this year. So it looks like it's a lot of things here, but I want to, depend on, what's your background. So you might have been already working on some of this. But here is interesting thing here is we observe that the future of vehicle computing is going to have 4 tiers here. So as we more and more moving to the autonomous, sometimes people call it automated, driving or self-driving, driverless, and etc. The basic idea is now vehicle, you have a lot of passengers sitting on the vehicle, is you're going to leverage the vehicle to do some computing here. So depending on where you are, for example, let me try to see that if I can, I noticed that sometimes I can, remote control. Do I do remote control? Okay, sorry. Okay, that's fine. So as you can see here is the core of this idea is you have a 4 tier. So starting from let me starting with a vehicle, okay? The next and last one, in the red color. So in the vehicle, for example, in the previous talk, that was a typical example is you're gonna have the things you are running on the vehicle and then doing the computing here. Most of the computing probably will be done on the vehicle. However, in case sometimes you feel like the vehicle is not powerful enough, so you're starting either asking the other vehicle, we call the V2V, or maybe you were starting talking to the edge server or, some including roadside unit, cellular tower, and etc. You were doing this V2I. V2I could be a V2 roadside unit, or maybe you're going to be doing all the way to the cloud. So this has been quite familiar these days when the people are talking about the connected vehicles. But there's other things, because if you think about this, when the vehicle itself is becoming more and more powerful, and then there's no drivers here, that means this vehicle could be running on the road, 24/7. So before, most of our passenger vehicles, when we drive that, I would say utilization for most of us, normal people doing the daily, driving from the home to the school or to the company, your vehicle's utilization probably less than 10%, right? because when you park in there, you're not doing anything. You basically just park there. But if you're looking for the future, so even when the vehicle is parking there, they can also still be a very interesting computing platform. So that was something I want to, talk, today, that we need to change our mind. Vehicle is not going to be just a computing devices while the vehicles is in driving mode. Even the vehicle is parking there. Some of the companies already done this. When you get home, you can do when you do the parking, you can do the upgrading. For example, the software updating. But if you're looking for most of the vehicles today, the updating is pretty straightforward. Except the Tesla, most of the other vehicles is very updating like a map. Very simple stuff. But then you can think about that. Even when I give you one scenario. For example, in many cities, when you parking your car on the street, right? So you are living on a very high-rise, apartment somewhere, like in San Francisco. In this case, when the UPS or FedEx, when they want to deliver stuff to you, actually, they can deliver your package to your car. Even your car is parked there, but assume somehow you already been authenticated. So you give the UPS driver the power that they can open your trunk, and then they can put in your package in the trunk, and then they will be delivered. So this is very convenient for you. You don't need to go to other places, lock your door, and etc. So this is just to show you an idea that because a vehicle will be in this case, the vehicle will be like a computing equipment, computing device. You can even more think about like a mobile computing platform will be with our human society for the future. So that was something we are arguing here is the vehicle will be, no matter it's driving or parking, there will be as a computing platform. And then there will be computing platform and the more mobilely moving maybe 24/7. It could be somebody else's vehicle. It may be your vehicle. So there is a lot of things going to happen. That's going to change the landscape of vehicle. For example, if you think your vehicle right now, the utilization rate is less than 10%. So if I tell you that if you let your car driving on their own in the community, so you can make some money, and the money will be definitely enough to cover your either the battery charging or maybe even the older gasoline. It doesn't matter, but you can also contribute to the society. So you might be starting leverages this, right? This is very similar to in the computing science back to the earlier this century, 2000. People are talking about using peer-to-peer computing because your computer anyway is idle at home, so that you can contribute the resources to the market, and then you can do some work. Amazon even have some interesting mechanism allow you to do this stuff. So this is going to be happening on the vehicle. That's our vision here. So hopefully I'm spending quite a lot of time on here to trying to share with you our thoughts about that. The vehicle computing will be very different from what we are talking about today. They can do a lot of things, based on this mobile computing platform. In the future, it might be possible that most of these companies, today's OEMs, they actually make more money through this computing equipment on that, providing more services, because they imagine that, for example, Toyota, right? Toyota have about more than 100 million vehicles globally. If all these vehicles can be used for some purposes, like to attack some climate changing, this type of computing, it could be a very powerful platform. So that was the things that I want to throw out to you guys. So in order to answer this, you might wondering that, hey, you talk about vehicle computing, sounds interesting. We need a definition here. So that was a definition we come out last year when we wrote this short article. You can think about it also enabling technology, allow computation to be performed on your CAVs, which serve as a computing platform for multiple CAV-related services. It's quite general, but that was something we are talking about. We're not talking, vehicle computing is not necessary for the transportation, driving purposes. It could be to a lot of other things. So that will hopefully give you an idea. So this was one of the vehicle that our lab, we have been putting together, a design and assembly together. For those of you working in this field, that, vehicle alone It's not really cost too much, but it's really the sensors. So this was showing you that why is this going to be changing. So this, even the cost model for this particular vehicle, in our case, the vehicle itself only costs 1/10 of the total cost of this platform. So that's why I'm talking about that. It's driving us to have to rethink about this. If I put in 90% of the cost on something else, then there must be we need to think about a usage to justify this. So for example, sensing around, I can assure you that, city of Detroit, we're running a vehicle every week, driving around the city to collecting the latest information about the hydrant, the traffic lights, and also those pools, are they working properly, and etc. Constructions, etc. That was another example. This already being more. Imagine this is an autonomous vehicle. Then you don't have anybody, right? Just driving around, collecting the data, and then go back to for the city. But the purpose is purely different. It's for the city, urban planning, infrastructure, even for the emergency, and etc. So the reason why is because it's coming with all this, sensing, perception, and decision. However, this is not really for the ADAS or autonomous driving purposes. This is purely for something else. So that was the idea that I want to share you that where this idea coming from. I can't just share you this concept, but we need to ask ourselves why we thinking about this. The other reason was obviously you probably already, since you guys are working in this field, you already heard about this. A autonomous vehicle generate a huge amount of data. This was an estimation from Intel, but in the reality, if you're looking for more, the vehicle right now is running on the California highways, getting the permissions, they actually cost much more, the power and this, the data they generated. The reason it was because of the reliability issues. Okay, so here is a data that I got from Dell, but I'm not sure that where this originally come from. Probably some of you might be here already contributed to this. So by 2025, the vehicle, the data generated by this ICV, in the Azure, normally they call the intelligent vehicle, intelligent connected vehicle, generated contribute 17% of all the data globally generated. So that's a huge amount of data, and then many of this needed to be, processed on the vehicle, right? So that we already seen that. So if you're looking for edge computing in the last 5 years, so the field already recognized that, okay, basically it's a 3-tier computing model. And then here we show that the CAV is sitting here is because we are using IoT on the left side. I'm gonna using an example to show you here is, for example, in the for the body camera wielded by the law enforcement, police officers. So when the police officer, when they left their vehicle, go to the real scene, so their body camera is a camera, right? They're gonna do the real-time processing and here, but due to the limited power, so most likely what happened is the camera on the wielded by police officer gonna sending back the data to their police vehicle, which is in the middle here, serving as an edge, and then do the processing, real-time processing, so that they can send him back enough. One of the example, we have a project with MIT Lincoln Lab, funded by the NIST, is we're talking about if the camera detects there is a risk, something is not safe for the police officer, and then this decision will be made on the vehicle, and then you will send him back that, for example, vibration of the body camera to the police officer, and then they realize, oh, something might be in danger, so that they will be in the high alert mode and etc. So this is another way to do this computing, but the car was parked there, and then it's serving as an edge. So in that case, car itself is an edge. But in many cases, in the CAV we're talking about, car is serving on the left side. They will rely on cellular tower, roadside unit to be as an edge device. But in general, that was a 3-tier in the computing model here. So that was the how do they supporting this type of this IoT in the ITS. So next, I want to talk a little bit about how do we do this work. That now obviously it's edge intelligence has become putting into our horizon in the last few years. And then here I want to show you that the figure compared with give you more nuts and bolts about what is really we talking about edge intelligence. So if on the left side you see that traditionally in the cloud, so you have this very powerful server software framework like a PyTorch, TensorFlow, and then you have a very intelligent algorithms. Now we want to run it on the edge, for example, on the vehicle in that side. So you can see that there's similarly have a 3 tier here, but 3 layers. But you can see that most of them are slightly lighter version. For example, TPU, and you have different type of this Intel computing stick and etc. On top of that, you have this lighter version of TensorFlow, TensorRT, and etc. On top of that, you have different pruning algorithms, and maybe you have a different even more simplified algorithms that can be running on here on the edge. So that was putting in the reality what does edge intelligence really about. That's what the people right now is working on this. So this figure shows that in the reality for the IoT in these cases, you're going to run in edge to cloud collaboration. You also have the edge to edge collaboration, and sometimes you're also going to need to do this edge things collaboration. So in these things could be imagine that you have a vehicle is running in the golf course. You have a vehicle running in the smart infrastructure, Industry 4.0, and talking to the drones talking to the vehicle. There's a lot of things going to happen. This is a very exciting area. So that's why I starting this talk is the vehicle computing is not what we're talking about transportation before. It's a wholly change the computing platform. So if you're interested on this, what type of resource scheduling and how do we deploy the tasks among these things. Recently, we two of my former students were working together, writing a very interesting survey paper going to be appear on that IEEE communication tutorials, and you can download it from our website. So that's covered pretty interesting, that what's the landscape today when you're talking about the resource challenges and etc. So then I will move on to the third part of this talk. That some of the work that we have been doing at Wayne State. Similar to Dr. Liu, that we're also very interested into looking for collaborations. If you are interested in have some questions, you can always, if you see, contact me. So here is our vision. This vision, I think all of us agree on that. So that you have the very traditional CAV vision. You have a vehicle, have the vehicle computing unit here, and then on top of the vehicle, you have we call it sort of a sand, kind of a TCP/IP style. You have some framework in the middle, and the lower level you have all kinds of data here, because the lower level you have different kind of data. I will talk more about in the next slides. So here it's not easy for you to read it because it's vertical. And then on top of that, you're going to support a different type of applications. So basically, we believe that the vehicle going to have 4 type of applications. I want to talk in the next slides. And then you have infrastructure. Infrastructure-wise, we call it X edge, but in this case, infrastructure also has their own kind of data, which is not something that the vehicle can easily see. So that you need them, for example, to give you the vision, or to give you the view. For example, when you want to make a left turn or make a right turn, if you cannot see that the pedestrian, then the roadside unit can give you a warning that, oh, there is a pedestrian here. You have to be you stop. That was again is some computing going to be happening on this side, and they're also going to be doing a lot of other services. And this is a typical. Sorry, my puppy was is barking here. Hopefully, you guys are okay with that. So there is more on that services. For the third-party services, will be deploying for the vehicle-related stuff, so they can also deploy it here. I will have some example to show you. So in order to support the previous vision, so back to actually it was like 3 and 4 years ago, we realized that one of the things is missing in today's vehicle is we're missing a open vehicle data analytics platform. So in short, we call it Open VDAP. The idea here is, if I'm a student, if I'm being asked to writing a code, for example, reading the camera from the data from the vehicle, and then to make some tuning to control something else. For example, control your light. The traffic, the vehicle light today is either on and off. So have we think about that? Can we make it adaptive, right? So this is a very simple project. That might be the future for all these vehicle lights. But how are you going to be writing this code? Writing this code is not easy because you need to right now you need to understanding the CAN bus, and then you need to sending a signal to the CAN bus, reading the camera data, and then bring the data back. The different camera providers have a different format, etc. So this will be a big challenge for the vehicle computing if we want to support that. So that was what we have been proposing here is very similar to the in the computer science. For example, in the smartphones today, they already have this for a long time, right? So what happens is if you want to writing a code for a smartphone, you don't need to reading all these things, each different hardwares. You don't care about that. What do you care about is there's a library here, either through iOS or maybe through Android framework. They already have a fixed APIs. So you can just call, say, I want to reading camera from the front. That's it. No matter what type of camera, you're going to give me this. So you could be tuning a different resolutions and etc. So that is what we are thinking. So OpenVDAP serve as a middleware here to encapsulate all the sensors data, including not just the sensor data, including vehicle data, from the traditional, from the control bus, from the weather, traffic, even social media data can be all included here. So you can easily call them. And then on top of that, you can do many things. For example, so we're starting with traditionally ADAS. I would say ADAS because the vehicle always care about OEMs. They care about ADAS or autonomous driving. That was, and there is another category is in-vehicle entertainment. And this became more and more important as the people sitting on the vehicle have nothing to do with driving now. And the third one is like a real-time diagnostic, still related to the vehicle, but it's more talking about the vehicle health statement. And then you have a lot of third-party applications. For example, Dr. News talk. So that work could be a perfect third-party application. Somebody could easily develop that for this human interaction stuff. You can develop that, and then you can sell to some people. People can download it, running on the vehicle, and getting more values. So that was the idea that we're talking about. But in order to do this, you have to you will have to know how to do the programming on this. So that was one of the work that we have been working on this. So with OpenVDAP as a platform, so our group have been working on quite a vertical space in here that including develop this Hydra 1 platform to supporting this. We have a benchmarking, machine learning on the heterogeneous platform, operating system for the vehicle, and then you have a collaborative cloud edge analytics, communication optimization, and most recently we're starting working on computing, communication, and the control core optimization, because we found out that purely on the computing and the communication is not enough, because eventually you have to consider the vehicle dynamics. Vehicle take time to react to your instructions. So you have to consider everything together. Then you can to getting this end-to-end latency. This is what we call the 4C. Is a computing, communication, control, coordination. That was the idea. So here, this figure shows all the platform we have in our lab, and pretty much all homegrown. That except that we cannot develop this for the fusion. But this the left side is an indoor autonomous vehicle for us to test our prototype, but running on indoors. And then on this right up is we call Zebra T. Zebra T is allow us to evaluation the things. It's a slow delivery vehicle, but allow us to do this on neighborhood, on campus, etc. It's a very slow speed, no risk. And then the last one is when we develop some real stuff running on the road. So we're going to be starting using this Hydra platform to running on the highway and the city road. In addition to that, we also develop some edge server. You can consider this as edge server, but it's serving more these purposes. Well, with thanks to those industry partners have donated this different kind of communication layer and the computing layer here. So we can do Wi-Fi, LTE, DSRC, most recently have a CV2X. To allow us to evaluate the vehicle, talking to them, to evaluate the different platforms. I still have like 7 minutes here, so I can give you a little idea we have done on this leverage these platforms and the ideas we have been doing here. Now, one is what we call the E2M. It's called energy efficient middleware, because assume that if you are on the vehicle, no matter if that is in the electrical vehicle, in battery powered, or is in the gas powered, you always want to minimum the number of power energy you're spending on the computing itself. So right. So here that's the idea that I want to say that we have a paper published in 2019 in the Edge Computing SEC conference. So we have been working on this, trying to coordinate the events. Right now, most of these applications people develop for the vehicle, none of them actually coordinate. But as an OEM level, you might want to coordinate this. Otherwise, you will be wasting a lot of this energy here. So the results shows that we have been showing that the sensing itself equipment costs a lot of energy, and then computing also costs a lot of energy. Together depending on what kind of road you are talking about. Together they might contribute about 30% of total energy on today's vehicle. So if we can reduce this, for example, by 50%, then you can save 15% of the total energy or every charge. For example, in an electrical vehicle side example, that can save a lot of that energy here. So that's just to show you an idea that we have been doing. The other thing is I talking about the real-time diagnostic. So collaborating with another company, so we collecting the data from driving behavior, VCU, MCU, and the BMS, and then we're using this to study looking at that how the driving behavior going to impact that the charging and discharging behavior, so that we can detect if there is early failure of these cells, for the battery. We demonstrated that there's a very strong correlation of your driving behavior and the battery failure prediction. So that was another one for the real-time diagnostic. We actually developed this running on the multiple vehicles coming from the same company, and then that they can we call it clone. But later on, you can just think about it is like distributed learning, but you don't need to do this in the real time. So that the same vehicle coming from the same company, you actually can deploy this model and then using the local learning and then gradually to detect the failures and etc. And then there's another one we call the P-beam, is doing cloud edge, personalized driving behavior, sort of related to what first talk is about. So this idea is we believe that every individual, the driving behavior are different. So we need to deploy this personalized learning behavior on the local vehicle so that this can be related to the insurance company, can be used that to do a lot of things. Driving behavior is a very important component for the vehicle related. The next one here is we're talking about vehicle edge. Cloud is one of the work that we have been collaborating with the Bear Labs. The idea is trying to reduce the number of videos that you really need to be transmitted from the vehicle to the edge or the cloud. So we using the technology called the compressive imaging. So right now, the best what we can do can reduce this traffic by 20x. Reduce significantly. You don't need to apply this machine learning on this original image at all. What you can do is you can compress this about 20 times. And then you can apply this machine learning algorithm on it, and then the accuracy is pretty cool here. So if you're interested, this paper also available online that we have been talking about. So the last one that I want to show you here is the one I mentioned a little bit earlier, is how do we detect that using a vehicle as a computing equipment, you have a dash camera can detect the environment these police officers are surrounding, but also the body camera can send him back to the vehicle to do computing on the vehicle. So you can do a lot of things, sending back to the we call the auto VAPs, for these public safety vehicles. And this was used as one of the reference architecture for the NIST. Potentially future vehicle can do a lot of these things to integrate with surrounding environment. So right now we have been actively working with a lot of companies. Some of you might be seeing your company's logo is also here. So if that's the case, I really appreciate your support. And we are also working with the city of Detroit. We have access about 400 traffic data here that allow us to looking at that, how this traffic is related to this computing and etc. So I will stop here that basically is hopefully the key point for today for this talk is about vehicle computing is coming. Let's not just looking for vehicle for the transportation purposes. A vehicle for transportation, let's assume that it's already there. So what's next? So that was something that I would like to share with you. So all these papers I mentioned here is available on our the Car Lab website. And if you have any questions, more than welcome to show me an email, and I will be happy to talk with you. Thank you.
Thank you very much, Professor Shi. Actually, I think we have several questions in the chat box, which are really good questions. I can ask on behalf of them. So the first question would be, would you mind elaborating on the major constraints of vehicle computing? And also, what will be the bottlenecks to deploy edge computing technology in our transportation systems?
Okay, well, thank you. The first question is that I'm sure there might be multiple. Based on my feeling today is there's no good. First is I'm a computer system researcher. Okay, the first thing is how you're going to be writing code here. That's always the first thing to my mind. That if you don't know how to writing a code, if there's no such a framework available, this will not be moving any further. Similar to the cloud computing, MapReduce was come out in 2004. That's why cloud computing became a blue zone after 2005. Similarly here, we need to have a programming model that can make sure easier for the students, for researchers can write in the code. That was the first one. Obviously, there is many other constraints. For example, when you want to talk about this, the vehicle talking to vehicle talking to the environment, the communication. The other thing which I have been really involved in the last few years is the communication itself. Although the community is talking about communication seems like everywhere. But if you are doing this, you will realize, okay, Bluetooth, VSC-V2X, DSRC, and LTE or 5G. This network, first of all, is not very reliable, right? So we have run some experiment published in the Hot Edge last year. You can see that the packet will be dropping significantly. So how this we are talking about IoT talking with this vehicle itself, or vehicle talking to the roadside unit, is a big challenge. So every time when I have a chance talking to the IEEE Communication Society, I always told them, you guys need to working hard. For me, I think that computing is much easier to use today, but the communication not there yet. So that's the second. Well, there's some other things we can skip that. So go back to the second question. You are asking that how deploy the edge for the transportation. I think it's already there. For example, Zren's group. That we Toyota, and then you can see that many others has been putting a lot of effort on the connected vehicle. Here, I want to distinguish these words. Although we're using that connected, autonomous, and always using CAV together, connected vehicle was very different from autonomous driving. So, in other words, autonomous driving don't need connected. Most of them, they are not connected at all. So we need to distinguish this concept. So with that, then you will see that it's much easier when you can start doing some stuff. So for connected vehicle, people starting doing quite a lot, computing stuff. However, the challenge is, again, programming, because most of the companies today, they introduce their own proprietary kind of software. So when I can show you when we starting this OpenVDAP, when I talk to some OEMs, they say, oh, I don't need that. But if you today, as of 2021, you can see that, almost every single big OEMs already come out with their own version of something very similar to OpenVDAP, because they realize that they need a program, talking to that. So I think that was a challenge, unfortunately, because a different company have their own platform. And that was the original vision. I wanted to have something can publicly available, people can download, and then you can easily deploy it on your own vehicle, can try that. So we are almost ready to release the first version of OpenVDAP, but still reading the canvas, reading to the different like automotive Ethernet, all these things was a challenge. That Okay, I know I was taking too long time, I guess.
No problem. I mean, for interest time, we can switch to our second presentation, but Professor Shi, if you don't mind, you can go to the chat session where we have 3 more questions. Maybe you can answer them in the chat box. Very good questions they are.
Yeah, I see many of people starting to ask OEMs on that. What do you think will dominate the vehicle computing market? That was, can I try to answer this?
Yeah, you can do it quickly. Yeah, sure.
Okay,
No
yeah,
problem.
so sure. So that was a question I always have people, because I'm from Detroit, right? So that I would say that whoever the company who is open their mind, and then that they're willing to embrace the different sensors and this stuff, they might be going to be the winner of this. If they're all still doing the old school, keep everything proprietary, one day they might realize that they might be lagging behind. So that's just my expectation here. All right. Sorry, I will try to answer some of your questions on the chat box. Okay.
Thank you very much, Professor, for very good presentation. Thank you once again.
Thank you. Yeah, bye-bye.
Okay, so our next speaker will be Professor Marikopoulos, and yeah, I see your screen. Dr. Andreas Marikopoulos is the Terry Connor Kelly and John Kenney Career Development Associate Professor in the Department of Mechanical Engineering and the Director of the Social Technical Systems Center at the University of Delaware. Prior to these appointments, he was the Deputy Director and the lead of the Sustainable Mobility theme of the Urban Dynamics Institute at Oak Ridge National Lab and a senior researcher with General Motors Global Research and Development. He received a diploma from the National Technical University of Athens, Greece, and his master and PhD degree from the University of Michigan, Ann Arbor in 2004 and 2008, respectively, all in mechanical engineering. And Professor Marikopoulos, you can start your presentation.
Great. Can you hear me well?
Yeah, very, very clear.
Great. Thank you, Ziran, and thank you all the other organizers for inviting me to this very interesting workshop. I have enjoyed the presentation so far, and I'm pretty sure that the rest of the presentation will be quite as interesting as the first two one. So today, what I plan to do is to talk a little bit about how we can develop optimal control techniques that we can use in order to coordinate connected automated vehicles within particular traffic scenarios. We live in a world that is changing, and we're about to have several paradigm shifts. For example, we're about to depart from conventional vehicles with internal combustion engines and move on to pure electric vehicles, which will cause a significant cascade of events and changing of the landscape of the infrastructure. We will see a lot of charging stations, share information, different type of challenges and problems that we will have to address pretty soon. We will have to coordinate, energy demand. We have to coordinate different travel demand. On top of that, the landscape of the cities will change with more renewable resources. And as this all happening, pretty soon we'll have connected automated vehicles that will share information, create a lot of data. So all these are, a picture of what is coming in the area of emerging mobility systems. And my point here is that we need to develop advanced control techniques that will be able to address those challenges. In this picture and this vision that Siemens put together, and we also can agree that this is happening, you can see different problems, and all these problems refer to cyber-physical systems. And the idea is how we can develop advanced control technologies that can help optimize these cyber-physical systems. What I'm trying to do today is just to focus on connected automated vehicles and show you some work that we have done in this area in order to optimize traffic flow when we have connected automated vehicles. I'll show you some simulation experimental results, and then I'll discuss a couple of directions for future research. Before I get to start, I need to acknowledge the support and contribution of my students. This is only the PhD students that you can see in the on the picture. There are a bunch of other master's students and undergraduate students involved in our research activities. The goal of my lab is to enhance understanding of cyber-physical systems and develop the theoretical framework and control algorithms that can make these systems able to realize their optimal operation while they interacting with the environment. The emphasis on our applications is on emerging mobility systems, connected automated vehicles, and so forth and so on. And for this matter, we have developed a testbed, a robotic scale smart city, 20 by 20 feet or 6 by 6 meters, which includes 1 to 25 scale robotic cars. We can use this city that and replicate some of the traffic scenarios that we can encounter in real world, and we can use this city to go beyond simulation and prove some of the concepts. So this is a test bed in between the simulation and a real world test facility. We have also implemented the capability to drive those robotic cars so that we can have a mixture of connected automated vehicles and human-driven robotic cars. So we have cameras in front of the vehicles, and we have integrate these vehicles with driver emulators, so the students can drive the cars through a monitor, as you can see here, and interact with other, cars which are supposed to be connected automated vehicles. So with this framework, we were in the position to sort of, capture, what we have today, the state of the art, and go all the way through more futuristic sort of approaches. Now, what we came to realize is that once we go to the physical test bed, we do have certain challenges to debug our control algorithm. So we created a replica of our physical test bed in a digital environment. So before we go to the scale city and do some work, we can go first to our digital replica, develop our control algorithms, test them, validate them, and then once we figure out all the details and decode, then we can move on to the scale city. This saves a lot of time through the process. We also have a driver simulation testbed with 6 driver simulators that we can use within any commercial software. We use Prescan and vSim. And replicate any city in the world that we can want to explore. So that was a little bit of introduction about my lab. Over the years, I have the chance to work on different problems in the area of mobility and transportation. I started with developing control algorithms on the powertrain of the system, and in particular, how we can make the engine learn the driver's driving style and eventually optimize its operation with respect to the driver's driving style. Then I move on to hybrid electric vehicles and plug-in hybrid electric vehicles and how we can optimize the powertrain of these systems. And for the last 10 years, I've been working on connected automated vehicles and how we can use shared information and automation to improve the transportation efficiency. This is the topic of my discussion today. I'm going to try to focus and show you how we can use this shared information and automated features in order to improve efficiency in scenarios like this. In scenarios that we have potential conflict between the vehicles, like intersections, merging roadways, roundabouts, and so forth and so on. Fast forward, before I get to the technical details, let me show you the progress that we have made so far. We've been able to develop control algorithms that can help coordinate vehicles on intersections. We have also expanded this and include multiple intersections in an environment where we have 100% penetration of CAVs. We have also implemented this in scenarios like merging roadways. It's quite straightforward once you solve the problem on one particular traffic scenario to translate the result to different scenarios. We have also considered roundabouts. And then once we put all this, toolbox with the solutions for each individual traffic scenario, we can put all them together and address a corridor. This is the case that we have worked on a corridor in our scale city that includes, a roundabout, an intersection, and a merging roadway. So you can see how all the vehicles can coordinate with each other and cross these potential conflicts without stopping over driving. So with this scenario, we can, in other words, visualize in a scale environment, although how a smart city would look like in the near future. And then at the same time, we can also encounter some of the challenges that we can encounter in the physical world before we go to a physical testbed. And we did that when we, with our test vehicle, and now the A3 plug-in electric vehicle that we considered during a recent ARPA in NextCar program project. So with this project, the goal was to improve the efficiency of the Audi by at least 20% using connectivity and automation. So we were able to develop these technologies that I just show you and run the Audi in M-City at the University of Michigan. So we eventually had the Audi running in M-City within an augmented reality that they have implemented. So the Audi essentially was interacting with the virtual vehicles, as you can see on the left, and going through different scenarios like speed harmonization, roundabouts, intersections, merging roadways. So we were able to put the Audi in the field, interacting with virtual environments that create a peace of mind regarding the safety concerns, and then address all these problems. So now let's take a deep dive and see how we can potentially address this problem. I show you a little bit of the outcome, the final result. I'm going to go back up now and show you a little bit how we can get to these areas. Just to show you, to go through these ideas, I'm going to reference an intersection, just because an intersection has some sort of challenges in these cases. The same analysis, the same exposition can be applied to other traffic scenarios. So we consider an intersection, and let's assume that we have 4 connected automated vehicles approaching the intersection. Apparently, if they keep going, they will have to address some conflicts. So the area within the intersection that we can have a potential lateral collision is called merging zone. And then we define the control zone, which is outside the merging zone and within the proximity of the vehicle. So within the control zone, the CAVs can exchange information with each other and then identify the timing that they will be entering the merging zone at the center of the intersection without collision, of course, and without stop and go driving. So the idea is for each vehicle entering the control zone to derive an optimal acceleration so that to avoid collision at the merging zone and exit the control zone as soon as possible. Just to take a look at this problem, so once the vehicle enters the control zone, the vehicle needs to coordinate with other vehicles and identify the appropriate timing to enter and exit the merging zone, right? And at the same time, derive the optimal acceleration to cross the intersection. So if you think about it, this is a 2-level optimal control problem. In the upper level problem, we want to identify the optimal timing that the vehicle will be entering the control zone so that to maximize the throughput of the intersection. And in the low level problem, given this timing of the entry and exit of the control zone, we need to derive the optimal acceleration of the vehicle that can optimize fuel consumption. What I'm going to do now in the next few slides, I'll show you that we can start from the low level solution, the analytical solution, and reverse the solution and get formulate a problem that can identify the timing of the upper level problem. So essentially, we can translate these 2 problems in a single level optimization problem. And the reason that we want to do that is that, as you will see later on, the low level optimization problem is quite involved and cannot be solved in real time on board the vehicle. So we need to have a different way to address this. So in our analysis, we model each vehicle as a double integrator, enhanced double integrator, where P is the position of the vehicle starting at the entry of the control zone, V is the speed of the vehicle, U is the control input, acceleration, deceleration, and S is the distance of vehicle I from the preceding vehicle K, right? So this is the proximity sensor essentially of the vehicle. Now, somebody might argue, well, I mean, this seems a very simplistic model to capture the vehicle dynamics of the vehicle, and that would be a fair argument. Now, what we do here is that since we seek to derive an optimal solution in real time, we use a double integrator so that we can derive the optimal solution in real time. Then this solution would give us the optimal acceleration deceleration. And then a low-level controller, a PI or a PID controller, will use which has been designed, given the vehicle, the true vehicle dynamics of the vehicle, will track this optimal control input. So essentially, we translate the optimal control problem to a tracking signal problem with this approach. And this is the standard approach that all the OEMs follow in order to design ACC controllers. Now, the next step is to define the bounds of the state and controls, and as designated by the physical constraints of the system. So, for example, for each particular vehicle, we need to have a maximum braking and a maximum acceleration capability as designated by the vehicle, and also for each vehicle, we impose a speed limit from the time TI NAT that the vehicle enters the control zone until the time TIF that the vehicle exits the control zone. Next, of course, we impose the safety constraint. So the distance of vehicle I from the preceding vehicle should be always greater than equal to a safe distance delta I, which is also a function of the speed of the vehicle. And then we also incorporate the lateral collision safety constraint, where essentially assures that any vehicle I will not have a lateral collision with any other vehicle K coming vertical to the intersection. Given these constraints, we can formulate an optimal control problem, which is minimizing the L2 norm of the control input from the time TI NAT that the vehicle enters the control zone until the time TIF that the vehicle exits the control zone. That was the lower level optimization problem that I mentioned at the beginning. Given the initial speed of the vehicle, the initial position of the vehicle at the entry of the control zone, TI NAT, and the final time that is being determined by the upper level optimization problem and the position of the vehicle, and given all the subject to all the dynamic state control and safety constraints. Now, somebody might argue that, hey, you know what? You told us that you plan to minimize fuel consumption of a vehicle, and now you're minimizing the control input, the L2 norm of the control input. How is this happening? How is this related? Well, what we're trying to do here is to minimize the transient engine operation of the vehicle, of the engine. By minimizing transient engine operation, you essentially have benefits in fuel consumption. We can't really minimize speed of the vehicle. The speed of the vehicle is being determined by the driver, and we have no control over it. If the driver goes to cruise with a X speed, this is determined by the driver. What we're trying to do is to give this speed to the driver with a minimum acceleration and deceleration. So we're trying to minimize essentially the engine operation of the transient engine operation of the vehicle. Then once we formulate this problem, it's quite straightforward to solve it by formulating the Hamiltonian function. And if none of the state control or safety constraints become active, then we have a very nice closed form analytical solution of this problem that results in a very nice affine linear control input. And in this particular case, A, B, C, D's, and E's are the constants of integration that can be easily found through the initial and final conditions. However, if any of the state control or safety constraints become active, then things are getting really complicated. Let me show you what is happening. Let's say that we have no constraints, no constraints activated. So we have a very nice, the nice closed form analytical solution that I just showed you from TI NOT and TIF. If any of the state control or safety constraints become active, then we need to piece the constraints and unconstraints arc all together and satisfy the Euler-Lagrange equations along with the interior and boundary conditions. This will result in a set of nonlinear algebraic equations that we need to solve simultaneously and also compute the T-NAT, the junction point of these arcs. Now, let's assume that we get the solution. If this solution, again, the new solution, hit any other, activates any other of state control or safety constraints, then we need to repeat this process. And in this particular case, we cannot really hope for any closed form analytical solution. We seek for decent, gradient descent algorithms and numerical solutions which essentially prohibit any real-time implementation. So this is the case. This is just an example to give you a flavor of the kind of complexity that we can get. This is an example with a safety constraint, which once it activated, then it implies nonlinearities, discontinuities of the influence functions lambda and the discontinuity of the Hamiltonian. And for us to address these discontinuities, we need to adjoin the partial derivative of the constraint by a set of constant Lagrange multipliers pi, and attach them, adjoin them to the influence factor to the right of the junction point, and solve this simultaneously. So you can get an idea the kind of complexity that we can get. So instead of going this way, the idea here was that, okay, let's start with an analytical solution, closed form solution of the unconstrained case, the case that we have no stated control constraints activated. If you remember, we have a nice cubical polynomial function of the position of the vehicle, right? So if you essentially consider this particular solution, the control input, if you remember, was a nice linear nice linear affine function, right? And then we have also a cubic polynomial for the position of the vehicle. Now, the idea here is that if we reverse the position versus time, the optimal position versus time that corresponds to the unconstrained case, if we reverse this polynomial, then we can get the so-called time trajectory of the vehicle with respect to the position. So we get essentially at which time the vehicle is at its different position within the control zone. Now, once we have all the time trajectories of the vehicles within the control zone, any new vehicle that comes in can search within these time trajectories and draw a new time trajectory that avoid intersecting with any of the existing trajectories and minimizing the time that the vehicle will be exiting the control zone. Once we do that, once we identify this optimal time trajectory, then we can inverse back and get the equation, essentially the optimal position of the vehicle corresponding to the low level optimization problem. So with this idea, eventually we can solve both problems at the same time. So within this context, first of all, the first question that we need to address is whether this inverse function exists. And it turns out that this position is a real value function, right? And it is differentiable. It's also a strictly increasing function. So the polynomial function P is a one-one function. So we know that an inverse function exists. And as a matter of fact, using the Carton's method, we can compute the inverse function, the time trajectory of the vehicle, which look like this equation. And in this particular case, omegas are the new constants of integration, which are functions of phi. So if we now imagine that this is the time trajectory, this time trajectory gives us the time of the vehicle at its different position within the control zone. Now, if we evaluate this function at the exit of the control zone, then we essentially get the time that each vehicle will be exiting the control zone. And we can use this as the objective function that we want to use for the upper level problem. So essentially, if we evaluate the time trajectory at PIF, at the position of the vehicle at the exit of the control zone, so essentially we got a function, right, which is a function of phi's. So imagine that we have the time trajectory now, and we have the phi's that we can play around and shape up the time trajectory. So once we got the objective function that we want to minimize the time that the vehicle will be exiting the control zone, but at the same time, we have the phi's that we can sort of shape this time trajectory and avoid any collision with the other existing trajectories within the control zone. And now the next step is, of course, to identify all the equality and equality constraints. For example, we need to make sure that this function satisfies the boundary conditions, the position of the vehicle at the entry of the control zone, the position of the vehicle at the exit of the control zone, the speed, the initial speed of the vehicle at the control zone, and so forth and so on. And then also a bunch of inequality constraints. So, for example, we want to make sure that this time trajectory will not activate any of the speed constraints within the control zone. The entry, we don't want to violate any of the rear end or lateral collision constraint. And at the entry of the control zone, we need to have a speed which is less than the allowable speed of the vehicle in order to make a right or a left turn. Now, given this set of constraints, we can formulate our problem, which is minimizing the time trajectory with respect to the phi. So you minimize the time that the vehicle will be exiting the control zone with respect to phi. So find essentially the shape of the time trajectory that can achieve both. Two nice properties that we can get from this formulation is that we can prove that the objective function along with the quality and inequality constraints are all convex functions. So and this give us by applying the Salton conditions, we can show that there's no duality cap in the upper level problem. So essentially we can solve this problem in real time. We have implemented this in different scenarios. I'll show you some results right now. I show you already some results at the beginning, but we have captured also two intersections, merging roadways, speed reduction zones, and so forth and so on. So this is a scenario, the very first, simple scenario in simulation when we have multiple vehicles crossing the intersection. As you can see, all the vehicles derive their time trajectories and they can cross the intersection without stop and go driving, without any collision. Then we move to our scale city and develop this with the robotic cars. You can see now going through different directions how the vehicles can eventually cross the intersection without stop and go driving and with a safety constraint. And again, I want to emphasize that all the vehicles here are connected automated vehicles, and they all follow the same control algorithms by deriving an optimal time trajectory. And then we move off to our ARPA next car project Audi vehicle, and we first started on a chassis dyno on Bosch Farmington Hill facilities. So we put the Audi on the chassis dyno and went through a virtual environment with virtual vehicles. You can see on the left the baseline scenario when the vehicle doesn't communicate with other vehicles. This is the baseline scenario, so the vehicle comes to a full stop and so forth and so on. On the right is when all the vehicles are connected and automated, and you can see how we can eliminate stop and go driving compared to the baseline scenario. And this is essentially when we get the fuel economies. So these are some samples of the speed profiles. In all the cases, you can see that the Audi with our control algorithms eliminates stop and go driving versus the baseline scenario, and we eventually get benefits ranging from 14 all the way to 35% improvement just because we have eliminated stop and go driving with the vehicles. Then we move on to the scale, to the M-City at the University of Michigan. You can see now the Audi on the right be alone, but again, using the augmented reality of M-City, the Audi interacting with the virtual vehicles, the black vehicles that you can see on the left. On the top is the baseline scenario without communication, without connectivity and automation. On the bottom is when the vehicles can coordinate. So you can see the Audi coming up. This is the white vehicle on the screen. In this case, they have to come to a full stop. In this case, communicates very well and merges and crosses the merging roadway without stop and go driving. Although in this case, it stopped because there is a virtual vehicle ahead of it. So you can see the benefits. We use the same concept in the roundabouts at the University of Michigan. Here again, the Audi will come and have to come to a full stop and wait behind this virtual vehicle. Although in the bottom case, the Audi coordinates and crosses the merging roadway without the stop and go driving. These are some benefits of this approach. These are the benefits with respect to the travel time on different traffic scenario in M-City. This is from the field test on RAP when we have speed harmonization, when we have a roundabout, and for the entire corridor when we compare all of that and put them together. And also we have some energy benefits. So you can see how the Audi can improve the energy of the Audi at on-RAP, at the speed harmonization scenario, roundabout, and also during the corridor, at the corridor. So just to wrap up, we showed how we can eventually develop a framework that can help coordinate vehicles at different traffic scenarios. Essentially, we have transformed a two-level optimization framework in a single-level optimization framework that can be implemented in real time. As we speak, we're working on incorporating errors and delays in communication with CAVs. We're also working on different penetration rates. So we use CAVs to indirectly control human-driven vehicles. And at the same time, also we explore areas at the intersection of learning and control and see how we can leverage the benefits of both approaches to address these issues. With this, I would like to thank you for your attention. I'd be happy to take any questions.
Thank you, Andres, for this very in-depth presentation. And I noticed we have two questions, but before that, I have a quick question. And I noticed you mentioned that in the last slide that you are going to consider different penetration rate of CAVs, right? Because the work that you just presented are more focused on like 100% penetration rate of CAVs. But for like lower penetration rate of CAVs, say it's mixed with CAVs and human-driven vehicles, will you consider the different driving behaviors of those human-driven vehicles, or you assume they are homogeneous, they behave as a same
actually, our approach is agnostic about the driving behavior, so we can consider any driving behavior. What we're trying to do is we use the and actually we have just recently published a couple of papers in this area, and we have a couple of more in review. We use the CAVs to indirectly control the human-driven vehicles by forming platoons. So one CAV, essentially behaves in a certain way. We formulate the problem to behave in a certain way and creates a platoon of HCVs, of human-driven vehicles. And then let's assume that the human-driven vehicle wants to change lane just to avoid this sort of, slowing down of the CAV. It will bump up to another CAV which behaves in the same way. So eventually we create platoons of human-driven vehicles led by a single CAV, and then we coordinate the CAVs. We coordinate the leaders of this. So we can apply the same techniques, but now instead of coordinating single CAVs, we're coordinating CAVs leading a platoon of vehicles of human-driven vehicles. So this is one of the approaches that you can find in the literature, and it seems that it works really well. Of course, we have a long way to go and do different studies and identify the disadvantages or the limitations of this approach, because I can tell that there should be some limitations. For example, what is the minimum number of CAVs in the network that need to exist in order to apply this, right? We need to know what's the minimum number. Let's say that we have an intersection and with medium traffic volume, how many CAVs we need to have, right? So all these kind of questions that need to be addressed.
Understood. And here's another quick one. The smart city platform is very interesting. Where can we get more information about it?
So if you go to my website, we have, and you go to publications, we have a bunch of papers referring to Scale City. We just submitted an article in the Control System magazine that we go through all the features that the Scale City has. So we have, if you guys Google, and start from the lab's website, you can find several papers in this area. And we have details, including details information about the features of the city.
Understood. Thank you. And one last question. In the earlier part of your talk, you mentioned collaborations across simulators, scale vehicles, and real vehicles. Now, how do you guarantee the real-time synchronization issue across these different platforms, especially when you have complex optimization problems to solve?
Yeah, so this is a very interesting question. We haven't developed this technology. This is the technology that developed from Professor Henry Louis at the University of Michigan. So they have, he developed this augmented reality, and it's actually pretty precise. I mean, we did a lot of experiments, field testing with Audi in M-City, and we've noticed that it's pretty robust. So we could have different, first of all, we did the implementation of all the algorithms in real time. We ran the algorithms for the Audi in real times and for the virtual vehicles in real time. So the results were pretty impressive, but I cannot really comment on this platform because that has been developed by Professor Henry Louis, and I know that he has published several papers that describe the details about this.
Okay, got it.
To learn more about this, they can go to the M-City's website and Professor Henry Louis' website to find out more information about that. He was kind enough to let us use M-City in this platform to do it.
Got it. Okay, thank you very much, Dr. Manikopoulos, for this very exciting talk. And let's move on to our next speaker. Our next speaker will be Professor Alfred Chen. And yeah, I see you there, Alfred. Dr. Chen is an assistant professor in the Department of Computer Science at the University of California at Irvine. His research interest is network and system security, and the major research theme is addressing security challenges through systematic problem analysis and mitigation. His research has discovered and mitigated security problems in systems such as next-generation transportation systems, smartphone OSs, network protocols, DNS, GUI systems, and access control systems. Please take the stage, Dr. Chen.
Sure. Yeah, thanks for the introduction. So you can hear me, I assume?
Yeah, very clear.
Great. And the slides is on?
Yes.
Okay, great. So I guess hello everyone, and then also thanks Lateral for inviting me and introducing me. So I guess my angle is a bit different from the previous speakers, because instead of like looking at the performance or how to improve the performance of the autonomy, the connectivity, the computing. So I'm so from a cybersecurity background, so I'm looking at the security of these emerging technologies in the intelligent transportation domain. So just a little bit about my my group. Yeah, this is working. So my group's name is SGuard, Autonomous and Smart Systems Guard. So our grand vision is to secure those emerging technologies that can make our whole world more autonomous and also more intelligent. Our core expertise is the software and AI security. I'm more from the CS background. So we used to do this purely on the cyber layer, like we look at the software security, like malware in the smartphone systems, desktops, network protocols, web. And then now as the computer science technology has been going more and more into the physical world, so we are more looking at the cyber physical systems. And one of the core target is the intelligent transportation systems and autonomous driving. So in my research, besides publishing papers, we also pay lots of attention in trying to generate practical impacts. So for example, we will make video demos for those attacks we discovered, for the vulnerabilities. And also for the vulnerabilities we discover, we'll also report them to the corresponding vulnerability management agencies like CVEs and US CERT from US DHS, and also to the corresponding developers like Android, Linux, Apple, Comcast, Microsoft. And recently, as we work more and more into the security of the autonomous driving systems, so we also report to the those companies working on this autonomous driving technologies. Last but not least, so we also work on the intelligent transportation. So we also report and have some discussions with US DOT about the vulnerabilities we discovered. So today, I guess, it's under the topic of this workshop, so I will be mainly talking about our recent focus, the AI stack security in the smart transportation. So I guess, needless to say, there are lots of new technologies and on the autonomy and the connectivity in the so recently in the transportation area. So one of them, very prominent ones is autonomous driving, right? The AD, and also connected vehicle, which is on the networking stack or CV. I guess there are lots of the earlier the speakers have been talking about this, so I won't go into too much details into it. So I guess both technology has been pushed and actively developed by many companies and also the government. And then to study the security of the systems, so from the computer science the background, so my group has a unique angle, which is looking at the AI stack of this this AD and CV systems. Basically, the brand that makes them to make this autonomous driving decisions or transportation operation decisions. So this is the security of this AI stack is definitely very important, right? Because any like errors has been made, for example, like triggered by the attacker can cause very severe real-world consequences, right? For example, all these examples from like Uber and also from Tesla actually in California. And also there's a lot of research value from the researchers' point of view. So in this case, because this AI stack has lots of new design components, domain-specific logics, which makes interesting to see whether there are some new design challenges and also new security practice that can be introduced by this domain-specific AI stack. So I guess to start with, I will be talking about this autonomous driving, which is the main focus in the recent 3 years in my lab, which is I would say probably the most the fastest like growing I guess technology in this domain. So I won't introduce too much details, but just very quickly. So autonomous driving, to put it very briefly, is just to put lots of sensors into a vehicle and to make it drive by themselves. So if we put the sensors here, the goal of these sensors is essentially to sense the physical world, right? For example, the road, the front cars, traffic horns, stop signs, so on and so forth. And then with the data from this sensed physical world, and then industry-grade systems is usually following a modular design, like perception, localization, prediction, planning, to make the decisions. So in the perception part, so usually this is going through a the most important task is of course trying to avoid crashes, right? So crashing into obstacles. So this will go through this object detection to detect objects, and then in a single frame, and then doing tracking, object tracking across the frames. And then usually this will be done across different sensors, right? Multiple sensors, and then eventually goes through a multi-sensor fusion process to achieve overall higher accuracy and robustness. And of course, there are many other domain-specific tasks that AD vehicle needs to handle, right? For example, like lane detection, traffic light detection, traffic sign detection, so on and so forth. And then on the other side, another very important task is localization. And then some of these sensors, like LiDAR, can be used to achieve global localization, like on a map, by matching the point clouds. And then some other sensors like GPS and IMU, which is traditionally also used for localization, can also be combined together in a MSF or multi-sensor fusion process to again achieve higher accuracy and robustness. And with the decisions made by the planning, then this will be going to the control module, and then eventually going back to the physical world to cause physical world actuation. So here, when I mean the AES stack, I mean the right part, essentially the decision-making part that's making the driving decisions as before it reaching to the control module, like the intelligent decision-making process. So to attack AES stack, so I guess if we look at this diagram, so one fundamental source of attack is from the sensors, right? So for example, if I can tamper with the sensing process, I can definitely introduce some errors into this AES stack. So actually here for the sensors, I'm showing here like this 5 main sensors used in autonomous driving. So spoofing or jamming attacks have been discovered, actually on all of them, like has been demonstrated in the security community. And then besides sensor, another possible source is to go one layer ahead, right? So going to the physical world. So how about we can change the physical appearance in a subtle way and also stealthy way, so that we can also introduce malicious inputs into the AES stack. So in my research, I consider both in my recent years. So in this problem space, so before my group has started to work on this, so probably one famous example, I guess many of you might know, is the attack on the traffic sign detection, specifically on the stop sign. So in this case, what they do is that they take a state-of-the-art camera DNA model, like deep learning model for object detection, and then they add some malicious stickers or posters on top of it. So this is what what it will look like from a top-tier security conference. So as you can see, you add this malicious colorful stickers on top of it, then you can make a stop sign disappear, or you print this poster that does not really look like a stop sign for human, but then it will be recognized as a stop sign for the AES stack of the AD vehicle. So missing a stop sign is definitely very undesired, but ultimately this does not directly mean that you'll be having very severe road hazards or like crashes, because there's another module there with a bunch of algorithms, very important, trying to prevent crashes, essentially this obstacle avoidance. So that's why when my group started to work on this direction, we start from this module by looking at this this algorithm security in the obstacle avoidance sub module. So we first start by looking at this LiDAR-based object detection. So this is published in CCS and used in security, both top-tier security conferences. So what we did is that we performed the first security analysis and defense design for 3D AD object detection, because previously stop signs are 2D, right, like images. So this is the first attempt ever to look at the security of the 3D AD object detection. So we use an interesting attack vector called LiDAR spoofing. So I guess LiDAR is probably will look familiar, and then the concept is very familiar for the people here. I don't need to say too much. And then there's an attack that's leveraging this fundamental mechanism of LiDAR sensing, is called LiDAR spoofing. So essentially, you shoot some laser back to the LiDAR to inject points. So this is a figure I got from I cropped from a previous work published in a Harvard security conference. So as you can see, this is the room, and then if you shoot the lasers, so there's a LiDAR inside this room. If you shoot the laser from this angle, you will see this random the points. All these green dots are those injected spoof points to the LiDAR. But then if you look at this, so this point looks pretty sparse, and also not. The number is also very low. So the question we are asking is that, okay, so this can affect LiDAR, but can we actually use this to attack the autonomous driving AAS stack? So to do this, we designed a novel algorithm, which is a optimization-based method that combines LiDAR spoofing with adversarial machine learning. So I guess both are needed to this kind of the first combined attack of sensor attack and autonomous and a machine learning or AI attacks. So combine them, and we are able to successfully find that actually, if you control the spoofed points in a strategic way, you are able to spoof a fake phone call at the perception output, and which can cause emergency brake or a denial of service or DOS. So then moving down the pipeline, we further look at the object tracking. So this is essentially published at ICLR, a top-tier machine learning conference. So what we did here is that we performed the first security analysis for object tracking. And in this case, we used an attack vector that put a malicious colorful sticker on the back of the front car. And we use optimization, but in this case, the optimization design is interesting. It's trying to shifting the bounding box positions. And in this case, we find that if we carefully design the pattern, we're able to move a roadside object into the current lane, which can cause an emergency brake, or move a front car away, which can cause a crash. And then while we are working on this, and then try to dig into this, the security of this obstacle avoidance algorithms, many other groups also realized this, and they did many interesting attacks. For example, instead of just putting a sticker, how about just paint the whole car with malicious patterns so that it cannot be detected by the state-of-the-art object detection in camera. And also, there's another interesting work published in last year's CCS at top-tier security conference. So what they do is that they have a projector to project a fake human figure into the ground, so that this is actually Tesla. They can fool the Tesla to see a fake human, which can cause emergency brake. So and then while we're looking at this work, then we actually find a problem, right? So actually, all of this work are limited to a single source of AD perception, like for example, LiDAR-based AD perception or camera-based AD perception. But then if you look at this industry-grade AD stack, when they do this AI-based perception, so actually there's always a step after this single source-based detection and tracking pipeline, that they will fuse the results in order to achieve overall higher robustness in general. So because of this stuff, then so this actually generally adopted by production AD systems like Waymo or GM, Pony. And then usually this is combining a camera and LiDAR because camera can give you the texture and LiDAR can by nature give you the depth. So it's a very good complementary source for the perception module. So in this case, actually a very interesting question is that if we assume that not all the perception sources are what can be attacked simultaneously. So theoretically, that's always possible to rely on the unattacked sources to detect or prevent a single source attack, right? Essentially, all the previous attacks, if you do cross-checking, you should be able to at least find some problem. And then this is essentially the basic security assumption, like you cannot attack all of them. This is believed to hold in general. And that's why this multi-sensor fusion, or MSF, is widely recognized as a general defense strategy against existing attacks on AD perception. And this also makes us curious, right? So if you so rely on this assumption, so can this assumption actually be broken, especially in particle AD settings? So this leads to a recent work, which is just published in IEEE SMB, Tokyo Security Conference. So what we did is that we performed the first security study of the multi-sensor fusion, or MSF-based AD perception. And then we try to directly challenge this security design assumption. Like, we want to explore whether it's possible to effectively and simultaneously attack all the perception sources. And in this case, we start from light up plus camera. So the attack vector we use is interesting. So we use a malicious shaped adversarial 3D object, because essentially, for example, look at this. There's like a 3D mesh, and then by designing this mesh carefully, and then you're able to make it realizable using 3D printing. So it's able to mimic like benign objects on the road, for example, traffic corners or even a rock. And also, by changing the shape, you're able to simultaneously affect both the point cloud of LiDAR and also the pixels in images. So with this, then we can just put this this object in front of the road, and then just fool the victim AD system to fail in detecting the fallen obstacle, and then just crash into it, because it cannot see it in either camera or LiDAR. So I have a demo website, so I want to show a little bit of that, just to concretize what we have achieved. So you guys can see the screen, I assume?
Yeah. Yes.
Great, thank you. So we first did in-lab miniature scale experiments. So this is a LiDAR, and this is 3D printed traffic warrant. It's a benign one, and that's a reversal one. So as you can see, this reversal one has a very bumpy left surface, but then this will introduce the noises to the deep learning algorithm input. Yeah, so yeah, I guess if we are doing this in person, I actually have some small ones I can show to you physically, but then yeah, probably just this image is the best I can do for now. So this is this is videos on left camera, right? So right is LiDAR. So as you can see, this is the benign one. So it can be detected by both camera and LiDAR in a very successful way. And of course, right? So it looks pretty obvious. It's red, and also has like shade in LiDAR, which is of course, right? And then in this case, when we just replace it with the universal one, but putting it exactly the same place, and it disappeared in both camera and LiDAR. So in this case, we do the same movement, but then you cannot see it. No, I mean the model cannot let's see it, even though it's very, very, very obvious for human eye. So we also did it with a real car, and this is in this is we made a this is there should be a cube, and then after we do this 3D manipulation, it becomes like a rock, because rock has this can have this arbitrary shape and looks still seemingly benign. And as you can see, this is the rock, and then looks pretty obvious in human eye with this shade. And also this in the camera, this looks also like there's something there. But then in this case, it's the same. So we drive towards it, and then I cannot see in both camera and LiDAR. Right. So yeah, so there are more details about it. You can go to the website to see more information. And then this is also open source. You can also try it. And then So besides working on this obstacle avoidance, so we also look at this other remaining modules of perception for the lane detection, right? That's also interesting. So this one win a best poster award in ITSS, a top-tier security conference, and I got published last year. I actually got published just a few months ago at Using Security, another top-tier security conference. So here we with took a production lane detection DNN model, and then here one interesting question that we face at the beginning is what can be a good attack vector, right? Should it be general? Should it be fundamental? And then the problem is that so first this level 2 lane detection system. So they will have a region of interest, like OI filter, that's making the camera or making the model input to focus on the road, because that's not all it needs to find the landlines. But then the problem is that for attackers, so what on the road surface can be both seemingly benign and also possible to introduce attack vectors. So then we think about it, and then we find out one idea that maybe this, right? So because when we drive on the road, it's very common to see this this white stands, right? This 38 patterns. So it can appear arbitrary and also look very stiff, even though it looks very weird. And also because of this patterns that can be manipulated by the attacker, this can also introduce the malicious input into the camera input. So then how to deploy this? So one way is to use this, so we call this dirty road patch. So it's actually, this is an illustration. So you can pretend to be road workers and then put a patch on the ground and then and with this dirty patterns on top of it. And then we use optimization methods, and then we find that this can cause the victim to drive out of the current lane very quickly, like just within 1 second. Also a demo to make it concrete. So start from this. So we also start from a in-lab experiments that we set up this miniature road and also put the patch on top of it. So this is a the camera for a production the ALC system like this automatic lane centering systems. And as you can see, in the visualization. So once we put this patch so the detected landlines is just consistently deviating to the left, no matter how we move it. It's actually quite robust. So we have a lot more experiments here. And actually in the benign case, it's very, very robust. So because this is actually some of our colleagues and students, they're actually using this in their daily life. So on the right, this is the benign case. As you can see, even so, if you follow the same movement, you can see it's just very consistently. On the benign case, it's consistently very straight, and no matter how we move it, but then with the patch, it's being controlled by the attacker. And then we also try this in simulation just to see how less severe this problem can be. So for example, this is we can first see this maybe. So the patch is here because it's where speed is high, the patch is far away. So in this case, it's even hard to see as a patch there. But then we realize that it's already that deviating that very fast. Same thing can also happen on the highway. So also the patch is here, but then very quickly you are hitting the barrier. But the vision can only show the ALC, like the automatic lane centering system level errors, right? So in a real car, you will have, for example, automatic emergency brake, right? So maybe it can prevent you into a real crash. But we try this on a car, and as you can see, we put some dummy obstacles there, and this is the dash cam. And we do attack injection, and as you can see, it's pretty fast, actually. Very fast deviating, and then you can see, so you can hear some beeping. That's the pre-collision alert, but I'm not really applying the control. But even this alert is happening very shortly before the crash, like 0.74 seconds. making it very hard to actually react for human. So coming back, so this is lane detection. So we also get traffic light detection. So this is a paper published AutoSec earlier this year. So this is an interesting idea. So essentially, we take an industry-grade AD traffic light detection pipeline, and we specifically target a design called this ROI, region of interest, because this production AD traffic light detection systems, they want to use region of interest to narrow down the detection scope in the raw camera inputs in order to make the real-time speed to be faster. Then because of this, to locate this region of interest, you need to use localization. So in this case, we can actually use GPS spoofing to attack perception. So we found out that this can move the right traffic light outside of the ROI, which can cause any denial of service, or moving a wrong one into it, which can cause the red light running. So there's also some demo in this. And besides perception, we also look at localization. So this is another best proposal award from ITSS, and then published last year in Usenix security, a top-tier security conference. And then what we did here is that we take a state-of-the-art MSF algorithm, which is combining GPS, LiDAR, and MU, and then for the AD localization, and then we use GPS spoofing as the attack vector. So methodology is that we use upper bound analysis plus causality analysis. And we find an attack that I won't go into the detail, but I have two stages. It's a strategic GPS spoofing, because this is a single source attack. So to break fusion, it needs to be smarter than the blind GPS spoofing. So, but in the end, what we find out that is essentially the effect is that if you detect a tailgate, the autonomous vehicle for 2 minutes, that's almost always like 97% of chances you can find an opportunity to use GPS alone to break fusion and cause the victim to drive off road or to the wrong way. We also have a demo website, but I won't show it because of time. So this is so here all the yellow boxes are from my group, and then all of this are on the design level security problems. But we also look at the implementation level problems, for example, bugs. So for example, last year we published a paper in IEEC, a top-tier software engineering conference, to perform the first comprehensive study of software bugs in the AD systems. So so before I move on to the connected vehicle, so this is essentially, we also did this responsible disclosure to over 30 companies developing or testing AD vehicles, and some of them actually conform to work on a fix. So coming back, so far it's all about autonomous driving, but I guess many of the people here definitely know that. So AI evolution also happens in the transportation domain, and one of the main force to push it is connected vehicle, because we are able to connect different elements and the agents on the road. So this can definitely enable lots of AI applications on top of it. For example, it can help autonomous driving as an actual source. It can enable smart traffic light or other infrastructure side intelligent operations, and also cooperative driving automation, like for the two. So of course, there's also come with security problems. So one source is that like many network protocols today, so connected vehicle technology can also be compromised, which can propagate into all these applications of transportation AI. So one likely, I would say a very realistic attack model is that the vehicle owners themselves can be malicious. They can deliberately control their OBU, like onboard unit, to broadcast spoof the CV data. This is a pure data level attack. So they can do this physically, wirelessly, or by malware, or they can compromise the OBU inputs, like using sensor attacks. But with this, they can actually be able to disrupt the upper layer AI applications. For example, previous work found that spoofing attacks can cause collision or significant traffic flow instability in platoon. And then building upon that, another work published earlier by my group is that we are the first to design a automatic vulnerability discovery methods with using model checking to discover automatically 14 new design flaws that can cause DOS or decrease the flow stability. And we also the first to look at the smart traffic light application domain, and then publishing the top tier the conferences in both the security and transportation. And then we are able to perform the first study of the infrastructure side connected vehicle systems. And then specifically in this case, we focus on the ISIC system, the intelligent traffic signal system, sponsored by US DOT. And then we use the CV data spoofing, and we find that even one single attack vehicle in the intersection can actually cause massive traffic jam. And the root cause is some new security vulnerabilities at the traffic control algorithm level. And there's a demo website you guys can take a look, but I won't go into details for the sake of time. And then following up on that, we also perform defenses on both the transportation infrastructure side and also the vehicle side. So to conclude, so my group is trying to actively developing a research space on the AS security in autonomous driving and smart transportation systems. So we have a website. You guys can go into it. It's just on the Google sites, CAV-stack. And then I believe personally, from the security community point of view, this is only beginning of this research direction, because as you can see, mostly we are on the attack side, right? We're trying to break those algorithms. And I think we should mainly focus on the defense side, because I try to close the loop and to actually improve this the security of this very safety critical systems. And to build a community, so I co-found a workshop called AutoSec, Automotive and Autonomous Vehicle Security, is co-located with NSS earlier this year, which is a top-tier security conference. And then we are trying to bring it to NSS again next year. So please stay tuned. And this is our official Twitter, so you can follow us to see the latest news. And I also serve as the general co-chair for the IEEE Safeties, which is co-located with IEEE SMP. Also earlier this year, this is another top-tier security conference, which is focused on more general the security and safety of IoT and CPS. And another interesting thing we do is that I help co-organize this first auto driving CTF. It's like a security competition, like a hacking competition, with Baidu in DEF CON. This is probably one of the world's most famous hacking convention. And then it's pretty interesting. So we create these challenges, and then those contestants have 24 hours to solve them. And then for example, you can create a malicious GPS trace, try to deviate a victim autonomous vehicle laterally, where you can implement a planning algorithm that's robust to some malicious the vehicle behaviors in front of it. And then in the end, we have like over 100 teams attempted, and then 93 teams got a better scores. This is the scoreboard. And then this is a hybrid event, so this is the on-site picture. So anyway, so of course I'll be happy to chat more, and I'm always open to collaborations. So this is my contact information, and then I think that's it for my talk.
Thank you very much, Professor Chen. And I do want to echo the first point that the second point at least here. It's just the beginning of this research direction, because I am new to this research direction, cyber physical or cybersecurity, but I know this is very important, and it actually aligns with our first question in the chat box, which is in your collaborations with the industry, how many focus do you think they have put on the security part? In her opinion, companies are paying so much more attention on how things can work, such as autonomous driving, instead of how things might fail, which is related to security. But she thinks the latter one is as important or even more important than the first one. So how do you think their focus is on for the industry?
Very good question. Very good question. So essentially, so you're right. So I've been in touch with the industry. So I'm as a security person, I'm trying to push this. But I think so far, more and more companies. I think before this year, in the last year, many of these autonomous driving companies do not even have a security division. So trying to fix this kind of problems. So starting just very recently, I guess within 1 year, I think 1 year, I can through my interaction with them, I heard that many of them are starting to actually putting together teams. And then, but so far, most of the people there are focused on the lower layer, like the still the traditional like cybersecurity in the canvas, like ECUs, not on the higher level. But then I can see more and more companies are trying to get into that into the AS stack. So I would say probably yeah, next year. So if we can come together again in the in this workshop, so I guess probably I would say I may find some companies actually started to push more aggressively onto the upper layer AS stack security.
Yeah, good to hear that. I think I agree with this audience. I think this is a very important element of CAV, right? You don't just make things work, but you have to think about all those fail-safe logic. What if things doesn't work?
Exactly.
Yeah, and the second point, I think you elaborate a little bit in your second part of presentation, and the audience was asking, besides the safety issue on the perception and localization sides, have you done any safety-related research regarding V2X? And I believe you did. And he would appreciate if you could provide a few insights on this topic, security related to V2X.
Yeah, that's actually a very good good question. So I focus more on the autonomous driving because that one has more growth in the recent years. So V2X, I think in the past years, I think it was not that active. So especially in terms of the real world deployment, and I guess probably today we still see probably 0 penetration rate. So that was the problem that I was kind of waiting for the good moment to more aggressive work on that. So, but there do have some mature less systems, for example, the smart traffic light. So that's why I did some research on that. And also the platoon, I think the protocols can also be studied early on because many people has been studied that. Actually, so last year, actually earlier this year at NDSS in the other side workshop, you can take a look. So Jonathan Petit, I guess the director of engineering at Qualcomm. So he actually gave a keynote specifically trying to address the V2X security problems. So I guess the consensus that is still early stage. We definitely need more research into it. He listed quite a bunch of probably 8 or even 10 open questions in this space. So I think it definitely worth more research efforts. I think probably even the center level research into it.
Okay, gotcha. All right, thank you very much again for your presentation, Professor Chen. Thank you.
Thank you.
Yeah, and with that, we can move to our next speaker, which is Professor Sharon D. Professor D is online, but she's also sent me a pre-recorded video. She will attend our Q&A session in real time in this chat. So Professor D is an associate professor in the Department of Civil Engineering and Engineering Mechanics at Columbia University in the city of New York. She also serves on the committee of Columbia Center for Smart Cities in the Data Science Institute. She received a bachelor's degree in traffic engineering in 2005 and a master's degree in transportation information and control engineering in 2008 from Tongji University in China. She received a PhD degree in civil, environmental, and geoengineering from the University of Minnesota, Twin Cities in 2014. Her specialty is travel behavior analysis and transportation network modeling. So here is her presentation. Share screen.
Hello, my name is Sharon D. Associate Professor at Columbia University, and today I want to talk about our ongoing work using physics-informed deep learning for traffic state estimation and the discovery of fundamental diagram. This is a joint work with my PhD student and postdoc, as well as my collaborators from Applied Math. Traffic state estimation is an old problem. Basically, traffic engineers aim to infer the spatial temporal evolution of traffic states using data collected from sensors. So the states can be represented by traffic density, speed, and volume. And the sensors include conventional loop detectors, probe vehicles, and overhead cameras. The most widely used method is the model-based. So that assumes all these data are generated from some underlying equations. And then the data are used to calibrate the parameters inside the model, such as the first or second order traffic flow model. Recent years, we are seeing a growing trend using machine learning methods, in particular deep learning, to directly discover the pattern from the data. However, training deep neural networks requires a large number of representative samples, but that's not the case for traffic state estimation. Usually, we have a small data set. How can we train neural networks using these sparse sensors? Is a question we want to answer for this research. And we found out that, okay, since the neural networks can discover patterns that are hidden in data that may not be able to capture by existing domain knowledge, but on the other hand, the traffic flow model can also provide physical constraints to the neural networks so that they can narrow down the search space during the training process. That's why in this study, we suggest to combine these two frameworks and develop a neural network regularized by traffic models. And we found out that it outperformed both model-based and data-driven methods, especially under the small data regime. We will demonstrate our finding using data generated from LWR models and also on real-world data set, NGCM. This study is motivated by a testbed that is deployed near Columbia campus for Internet of Things. So this testbed is called Cosmos. And this Cosmos testbed aims to validate the emerging communication technology, including Wi-Fi, 5G, and beyond, in an urban setting. This is a map of where these communication nodes are deployed. It actually covers from Columbia campus all the way up to the campus of City College of New York. This is the broad way you can see that connect these two campuses, and then there are several infrastructure on the side of the road mounted with communication nodes and also overhead cameras. And the research question here is, with all this data collected from IoT, whether we can leverage them to better understand how we can infer traffic states real time. Let me first show you a graph comparing the physics-based versus data-driven methods. So the x-axis represents the amount of the data used for each model, and the y-axis represents the amount of domain knowledge it requires to train a model. So physics-based model, we call the model-based approach or theory-guided approach, usually focus on the left-hand quadrant. So that means the physics-based model use very little data, very small amount of data, but they highly rely on people's domain knowledge and the scientific hypothesis. Machine learning models, in contrast, you highly rely on the data with little or no prior knowledge about the domain or how physics actually works. To combine them, we try to use an emerging framework called physics-informed machine learning, or PIML for short. So for this framework, it leverages the benefits of both physics-based and machine learning models, which is it requires only a small amount of data to train neural network, but can achieve a higher accuracy compared to both physics-based or data-driven models. And PIML has seen a growing trend in various science and engineering fields, such as earth science, fluid dynamics, and neuroscience. However, its application to transportation is still remain understudied. Let me first frame so how we apply PIML for transportation application in traffic state estimation. This is a partial differential equation. So rho represents the solution of a physical value of interest, such as the density, traffic density or traffic velocity field. And n of x is a nonlinear differential operator, and it's calculated using the derivative with respect to x. And the t and x are represent the time and space domain. And the goal of this PIML is to train a neural network that can approximate the solution of the original partial differential equation. How it works? So we can represent this neural network as n of theta. And the input of this neural network is t and x pair, which represents the time and the space domain. And output is rho. If this neural network can approximate the solution of the original partial differential equation, then we can substitute this rho value into a R function, and we call it residual. And if it accurately matches the original solution, then this residual should equal to 0. So then we can replace, we don't have to actually numerically solve partial differential equation anymore. Instead, we can just train this neural network. And then whenever we input one TX pair, the neural network would tell us what the value of rho is at that t and x. But how we train this neural network? So let me talk about the flow chart of this training process. So the neural network n of theta is our target. And we have some observation at a certain time and a certain time t and certain location x. So if this neural network is already trained, then it can output some value rho. And we also have observed the rho at those time t and x location. Then we can calculate the distance between these two values. That gives us a mean square error defined over the observation set. On the other hand, we can define a set of co-location points. So they also include a set of tx pair. And then when it's fed into the neural network, it also gives a predicted value of rho for each tx pair. However, we don't have observation on those tx pairs. Instead, we can feed this rho into a physics model. For example, here I use LWR as an example. In the equation U of rho represents the fundamental diagram we will use that define the mapping from rho to a velocity U. And then we feed the rho into this LWR model by calculating its partial derivative with respect to t and x. Then we can get a residual that is defined in the previous slide. Then we can calculate a weighted sum based on the mean square error and also the residual. We achieve a loss function. This loss function will be used to train the neural network. If the loss function is achieved at its minimum, then we know that this training process is done. The neural network we obtain is already the optimal one. If it's not, then we will update the hyperparameter theta contained in the neural network. Meanwhile, we have to also update the parameters that are used in the LWR model. Okay, this is the whole training process. And by the end of this training, we will get an optimal neural network. And the solution, the output of this neural network should approximate the solution of the original physics model. This is the idea, and I will demonstrate how this works using LWR as the physics. And you can see the upper part, those blue arrows represents the data-driven approach. And lower part, the red arrows represents how this physics-based flow is used. And then we integrate them to as one loss function. So you can treat this loss function as basically original loss function for neural network, but regularized by the physics. Okay, so now let's give you an example to demonstrate that process. We just use an ideal LWR model. The first equation is a flow conservation. The second is the fundamental diagram. We use the green shield here. And the domain X and T are defined. We also define initial condition and boundary condition. So we assume it's a ring road. That's why the density at the starting point and ending point are the same. And then we can theoretically solve this LWR system using numerical methods, and I provided the numerical solution here in the T and X domain. However, if we have some observations, these observation data we call the label data because it contains both the TX pair and their target value row. So this observation can be measured, say, on the initial condition. So at time t, assume we know all the traffic density along this road. And we know also the boundary conditions. For example, we place the two loop detectors at the starting point and ending point. And if there are some also loop detectors within the domain, we can also measure the density row in those fixed locations across time. Or we have another type of sensor like mobile probe vehicles, then we basically the density near the trajectory where this car is passing by can be measured. So this is the observation data we may have. And also let's introduce collocation data. We call it unlabeled data because we only select a TX pair. We don't know its target value row. The row will be calculated by the physics model we want to incorporate in the framework. So here, I assume we randomly select some TX pair from this domain. That is each point is represented by a black cross. So then we assume we have some observation data here. The red bars represent where the loop detectors are located. That's why we only collect the data for those fixed locations across time. And then we also have collocation points pre-selected. Then only based on these data, we can actually train a neural network following the step I introduced in the previous slide. And based on this loss function. And the MSE is the measure the distance between the predicted row from the observed row. And this R residual measures the distance of the how this predicted row far from the computed row using the physics. And the observation data can come from the initial condition, boundary condition, or any data points within the domain. So using this weighted loss, then we train the neural network, and then this is the result we get. So we can reconstruct the spatial temporal traffic density field using those sparse data. Okay, so this example demonstrates how this PIML works if we only have sparse measurements. Now we'll move on to the real world data set, NGSIM. But before that, let me talk about how we improve upon the framework that we discussed before. So this is the same training process for the physics-informed machine learning we discussed. The only difference here is because when we run this LWR model physics-based component, we have to also know what fundamental diagram the data has. But in real world, we don't know exactly what's the mathematical mapping from the density row to velocity yield. So that's why we replace it by another neural network we call the fundamental diagram learner, or FD learner for short. It's denoted as N of lambda, so it's a neural network parameterized by parameters lambda. And now this physics-based component is not an LWR model anymore, and we call it a machine learning surrogate model. So it follows the structure of LWR, and actually it only uses the information of localization. However, we use this neural network to approximate fundamental diagram. And then the training, when we update the lambda, so this lambda is not the model parameter involved in LWR anymore. It's also the hyperparameters used by the FD learner. And by on the end of the day, so what we will end up is the trained neural network plus this FD learner. And we apply this framework to the real world NGSIM data. Here we use the US 101 data set. The original data was collected using the overhead cameras facing that highway stretch. And we can aggregate those vehicle trajectory data and generate a ground truth traffic density map for that T and X domain. So this heat map represents the ground truth. And now we will randomly select some data. For example, we place 3 sensors along this stretch evenly distributed, and then only measure the density for those fixed locations across the entire time. And we gradually increase the number of sensors. And then using only this sparse data, we reconstruct this density field using the previous method. And here's the result. In this figure, the x-axis is the number of loop detectors. We gradually increase the loop detector. Basically, we increase the training data. And the y-axis is estimation error. And each line represents one model. And the blue one is just the pure neural network without using any physics. Lstm is the long short-term memory model. EKF is the classical method for traffic state estimation. Its full name is extended Kalman filter. And the PIDL, the physics-informed deep learning model, is the model we propose. And you can see this, the lowest curve is the performance of our model. It has a lower estimation error compared to other models, especially when you look at the small data regime, when there are only 2 or 4 loop detectors. Our model outperforms all other models and have a much higher accuracy. However, when the training data size grows, all these models gradually converge. The reason is because this deep learning model will more and more rely on the data, and they can better and discover the pattern from the data. And the right-hand side is another figure. The x-axis is still the number of loop detectors, but the y-axis is the ratio of beta over alpha. So if I refresh your memory, alpha is the weight in front of observation discrepancy. Beta is the weight in front of physics discrepancy or residual. So this ratio represents how much the physics play a role in training a neural network. You can see as the number of training data grows, the role that physics plays also diminishes. However, when there are only 2 or 4 loop detectors, which means there are very sparse data, and the physics play a bigger role to train a better model. Now we apply fundamental diagram learner, or FDL for short, to the NGSIM data. Let's look at the left-hand side figure. The x-axis is the number of loop detectors, and the y-axis is the estimation error. And we tried 4 models. The blue one is the LWR with the FDL. So there's no mathematical formula of what the fundamental diagram look like. And we try to learn at the mapping using another neural network. The purple is the LWR using the predefined 3-parameter green shields fundamental diagram. The orange is the ARZ with FDL, and the red is the ARZ with green shield fundamental diagram. First of all, we can clearly see that the models using FDL outperforms those without. Second, I want to draw your attention to these 2 lines, which is the LWR and ARZ plus FDL. So surprisingly, in the small data regime, LWR and FDL outperforms ARZ FDL. This is because ARZ is a more complex second-order model. It involves a lot more parameters to train and tune. So when there are only a few data points, the model tends to overfit. And in this case, LWR is easier to train and achieve a better performance. Right-hand side is the fundamental diagram. And here we focus on only 3 loop detectors, which is small data regime. The background, those black points are generated from the real data. X-axis is the density and y-axis is the traffic volume. Okay, this is the shape of the LWR FDL. So here we as I explained, there's no pre-knowledge of what a fundamental diagram look like. So we use a neural network to learn that shape. Then we can generate this curve. This is the standard 3-parameter green shields FD. And the orange dashed line is ARZ with FDL. And the red one is ARZ with the standard green shield fundamental diagram. If you look at the capacity part, so LWR ARZ plus FDL can better capture the capacity part. And if you look at the congestion part, actually the LWR FDL can predict a much better congested density than the ARZ FDL. So the blue line it's in the section with the traffic density is around 0.7. That's the value that is reasonable and also consistent with the value we estimate directly from data. So based on these 2 figures, we can say that for NGSIM data, LWR FDL perform the best, especially in the small data area. So that's all about my talk today. how we apply physics-informed deep learning for traffic state estimation. And also we present the joint estimation of fundamental diagram. Any questions? Hello, my name is Sharon Di.
Thank you, Professor D, for sending me the pre-recorded video, and I saw you also answer 2 questions in the chat box. Maybe I will elaborate the first question. You can answer that, and then you can go back to the chat box to answer the others, if you don't mind. The first question, and I think it's very interesting, is that the camera-based data sources like NGSIM can have a lot of noises. Does your solution require a high cleanness of the data source? And if so, how did you validate the accuracy of the ground truth data?
Yeah, so basically we assume the data we use is the ground truth. So, but you are right, it contains the noise, and also there's heterogeneity in driving behavior. So for this model, actually, I think this is also connected to the first question asked by Yilin in terms of the robustness. Basically, for this model, because neural network so far can only predict the average or the mean of a process. So here we have to assume the drivers behave kind of homogeneous. So that said, for example, if we have a same state, basically it's measured by the distance from the leading car and the speed velocity difference and the current velocity of the host vehicle. We assume they should tend to choose the same acceleration, but this definitely is not the case in reality. So we have to do some pre-processing of the data. So that's why this model, so it depends on how you measure robustness. If you're saying whether it can capture the distribution of these different state action pairs, the answer is no. So that's why we are trying to use like GAN to see whether we can infer the distribution also of our predicted values.
Okay, gotcha. Thank you. And I think there's another question I can quickly ask that. And it's a very general question, I think. Compared with traditional methods of traffic estimation in transportation engineering, why do you think are the pros and cons of data-driven methods that you just mentioned?
Yeah, so I think data-driven methods are definitely become more and more popular these days. But this is what this research is trying to address, that we think because we have developed this domain knowledge in terms of traffic models for the past decades. And the first traffic model can be traced back to 1920s, probably when Green-Schultz discovered a fundamental diagram. So we believe that we shouldn't completely abandon the physics-based models. Instead, we should integrate them or provide this more domain knowledge while training data-driven models. And we propose one method is using this hybrid paradigm. And basically, the physics can help reduce the searching space when the neural network is trained. But I can definitely say that the physics-informed machine learning is a promising direction to compromise the pros and cons of both data-driven and physics-based models.
Thank you, very clear. Again, thank you very much, Professor D, for the presentation and joining our workshop. Thank you.
Thank you.
And we can switch to our second last presenter. Let me stop sharing from my side. Okay, our next presenter will be Dr. Changyi Luo. And Dr. Luo, you can start. Yeah, I can see you. Dr. Changyi Luo is project manager and principal researcher in Toyota Motor Corporation in Japan. He's currently responsible for V2X product planning, development, and promotion in Toyota. In the past, he was experienced in research, development, planning, and evaluation for V2X, ITS, and other new technologies based on crash analysis. Dr. Luo, you can go ahead.
Can you hear me?
Yes.
Okay, can you see my screen?
Yes.
Okay, so I will talk about the V2X. Just now, I think the Professor Chen and Zirang have talked about the V2X is somehow slow now, and now we can see in US FCC we're still waiting for the how to happen next. EU we are looking at what's Volkswagen and anyone to follow next. And then China, we see now V2X is starting, but we're still waiting for more infrastructure and also more OEM to have mass volume put in. And Japan actually start quite early. Later I will explain, and I will tell you what is now happening and what's the challenge. And okay, so here is my background. Just now, Zero have explained. And I'm the project manager and the principal researcher in Toyota, Japan. And currently I'm responsible for the V2X product planning, development, deployment, and the promotion. So in the past, also I have some research in the research institute, research background. So it's not really usual in Toyota, but I'm also involved in the product planning. So I would like to share the industrial experience about how to move from the research and now in the product planning stage, what we are thinking about. So I would like to share what is happening here. Okay, so this is the outline of my presentation. Firstly, I think everybody knows what is V2X, but just simply emphasize it again. And there's, I don't know how many of you know, this actually a commercial service in Japan, we call ITS Connect. It starts in 2015, so already quite many years. So what's happened now and how many car equipped, that I will explain. And finally, I think you might be more interested in here and how to link V2X related technology to product reality. Yeah, because in our currently in product planning stage, how to using the new technology and to make a real product and deploy into the road. That is a challenge. Too many things need to be considered, and I would like to share the what is I was experiencing to you. So maybe in the future, everyone can make its own technology more close to the product. Okay, so what is V2X? So that we call case the connective autonomous, the mass and EV, and the first thing will be connectivity. So we believe the V2X will be the first part, the is essential technology for case business, so that in the future we know the future connected car can connect it to everything. We call it vehicle to everything, V2X, so that we believe its car is going to be smarter, safer, and more convenient. Here we can see to city, to other vehicle, to road, and to the pedestrian, and to other mobility device. So this is an image of what we are thinking about, what's a V2X. First is to get to connected. And for our Toyota, why we interested in to get connected, one thing is for our automotive OEM, we always think is safety, and it's a major concern of when we are designing any product and putting any technology here. And our goal of Toyota, we want to achieve the zero causality for traffic accident. We don't want any people lose their life or lose their family because of our product. So our approach is normally we integrate the three, we call the three basic elements for people, vehicle, and the traffic environment. Then for us, we pursue of real world safety, how we evaluate normally. Firstly, the things is what has happened before, the accident investigation, analyze. And through the simulation, development, evaluation, we try to develop the safer product. So that so towards the zero causality, how V2X, how the connectivity can help, except for the compared to other safety equipment. And here we can see a simple chart. It is how we reduce accidents The first, we can use autonomous safety system, which is, we can say, is use ADAS related, use LiDAR, this kind of technology. And others, we can use the vehicle and the infrastructure, the cooperative, the safety systems to reduce. And the third way to increase awareness of people. So this is basic the three approach we are thinking about. And for the effectiveness of each technology, we know like for the ADAS, the system, if we use the radar there, it's really effective to reduce like the rear end front collisions, which the radar sensor can prevent the collision in advance. But for some cases, such as the accident happening intersection with a motorcycle, with a bicycle, with a pedestrian, we found actually the V2X have some effects. The why V2X effective is because the main thing is they can reduce we call the non-line of sight accidents. You can't see the accident, you can't see the car is approaching, the LiDAR, they have the limit distance. The V2X might be another alternative to actually detect the accident and try to save your life. Okay, this is simple from the view. We believe it's safer, but actually behind it, we can see they may behind the motorcycle, pedestrian, and other cars. The V2X good things, we know each other's position, speed, direction, and the status. So actually we can do many things in ahead and to do the to help to reduce the accident. So here is the V2X service in Japan. We call it ITS Connected. Currently it provides V2I and V2V service, and the application is normally for safety environment and also for smooth cruising for VIP or emergency vehicles. And here is how we actually line up for the vehicles we sell in Japan. And currently, ITS Connect, we launched on October 2015. Currently, the volume until last month is about 2.3,000. Yeah. It's still the compared to the total volume of how Toyota sell a year in Japan or even in the world, it's really still a small number. But yeah, we are trying to promote the service, and also we are trying to tell the customers the value of V2X and try to spread it. And now you can see for Lexus is the more higher rank is they have the standard equips like LS, X is the standard. For some others can be options, and for this three is dealer options. And we also introduced into the evidence car in Japan. Actually, in Japan, the share of evidence of Toyota in Japan is about 80%. So actually, recently, the new evidence, about half of it is equipped V2X, so that when they send the patient into the hospital, they can tell the surrounding car, and the surrounding car receive it, can give it way, so that the ambulance can approach faster. And we have some research in some period of the road. We have tested with also the department of the ambulance, and it's have about 7% of the time we can reduce in current road. And here's the V2I and the V2V service in Japan. Now we provide such as the red light collision, the signal change advisor, and the right turn collision caution. And also we provide the V2V's emergency vehicles. Currently we have the 294 emergency vehicles in Japan. And now the intersection infrastructure now is about 113. Here we can see it's still quite low number. It's also one of the challenges for us, how to increase it to persuade the government to put more infrastructure. That is one of the challenges for us to overcome. And here is, let's show you how we put the device and how to show it inside of the car. We show in the metal part. where we have here to tell, because they have include the safety function. So we think put here, they can tell the driver more directly. If you put here, the driver may be distracted and may not to respond to the safety action easier. So we put into here, and here's some HNI you can see what we actually providing, and we use the sound as well to tell the driver when there's danger. And for the right turn collision, we have also two phrases of warning, which tell the soft warning and the hard warning tell the driver to be careful. And here I would like to show you the ITS connects the video so that you have some idea how actually we are promoting this kind of the technology, and what kind of aspects we are trying to sell the service. So I will put the video here. Okay.
Vehicle to vehicle. Vehicle to pedestrians. Vehicle to infrastructure. When they are all connected, daily life becomes safer and more secure. ITS Connect. It's already started. Supporting safe right turns. This service uses roadside infrastructure to detect oncoming vehicles and pedestrians in real time and presents this information to the driver to support safe right turns. This service is expected to reduce accidents when turning right. Notifying drivers of an approaching emergency vehicle. This service uses direct communication between vehicles to promptly notify drivers of an approaching emergency vehicle. Following the vehicle ahead more smoothly. This service integrates radar cruise control and vehicle-to-vehicle communication to enable smoother, safer following of the vehicle ahead. using information from traffic signals to promote eco-friendly driving. This service utilizes information from traffic signals to reduce unnecessary acceleration and braking to promote eco-friendly driving. This service is expected to reduce CO2 emissions. Vehicles, people, and society, all connected by ITS Connect. A service that makes life better for all, and it's already started.
Okay, so you can see this is how we Toyota try to promote the ITS Connect and the V2X service in Japan. And you know the service actually already come out several years ago, but still now we are still waiting for what the service actually can put more into the car and also in more regions. So here I would like to share the last part about how to link the V2X to product and reality. So how to be a product, usually in our product planning is we need, okay, what's the selling point? If it is really customer needs, customer will buy it. And important another is will be the price. Is the price enough compared to other products? Is enough to sell? Or for regulation, is the government going to mandate it? Or is any like assessments, new car assessment like NCAP will put on it? So just now we said in US, in EU, in China, in Japan, now there are still many challenges in the V2X. But as in the beginning of case, how to connect it with V2X, especially short range, maybe we need to consider how to make it become real. And often when we are talking about the vehicle and the infrastructure, who comes first is it become like egg chicken problem, who comes first, and yeah, it's always no real solution here. And also we know the technologies involving the 4G, 5G is coming to another new stage, and any new technology can overturn the old V2X. And now we know there's short range, long range, and how the technology improve and what's different product in the future we can actually put into the car. So in the setting point, we know there are many new things we are going to put into the car. The autonomous keys, LiDAR, 4G, in the future we want to put 5G maybe, and they want to put the V2X, and every kit, every equipment will be a cost. So that's how we balance the cost and provide to customer will be a challenge. The one thing we need to consider is the value to customers, the service versus the price. How many service can we provide to the customer and the customer will buy it? That was important things to think about. And the one thing we want to know, especially for V2X, because many people ask us, especially ourselves, always ask how many times the service may trigger. Okay, for emergency vehicle, 1 month, how many times can I meet? Or for safety, how many times can I meet? For V2V safety, and how many times can we meet? That will be another things to think about, because we know the penetration rate of the V2X car is few, then actually the service we can get is really limited. And also if the infrastructure is not there, there's really few times even impossible to get the service. So this is something about the setting point. And another things for safety equipment, how much to believe the V2X, the data there. And we know the safety equipment now For the car itself, there's ADAS there already, and in the future we want to put into V2X into it. And let's think, if we want to put V2X ADAS individual together or mix or using the V2X data to control the car as well, how to do it? If we know in ADAS, there are some service already provided in intersection in firmware collisions. If you want to combine it into V2X, we know the range difference. They can cross into the more the car the car before it. But how can we actually use the data, and do we really trust the data? Because we always talk to the ADAS, the product people, and they say they're not so sure, because the trust priority, we know for them, they trust their own server, their own sensor inside of the car. They trust it most. And the second, maybe they trust their own OEMs one. And then come to the other OEMs. How much should we trust it? And if we want to use their data, how much margin should we put in our safety? Because we know the perception, recognize, judge, and action. There are several stages for the car to actually act to prevent the accident. So where will ADAS be, and where will be V2X be? We have talked to the ADAS product people, and it's always not yet decided, and we are not so sure when can we integrate the ADAS and the V2X. But we believe it will be a future to integrate, but we are still looking at the which will be a trigger to let us to be integrated together. So I think we already run out of the time, so I will try to conclude the presentation. For the realization, we believe is have some use case we need to realize, to also some conditions. We know people will talk about the case last EV. If we want to make the EV reality and possible to all over the region or to the world to sell a lot, the first, we think the price compared to current cars should be cheaper, or at least not so different. And the charge time as short as possible. There are many stations, like gas stations, as well as exist. And the life cycle of the battery of the product should be longer or the same as the current car. So we know there are some examples for the condition for the EV to be realized. So how about the V2X? Will it be the price? Will it be the penetration rates? Will it be the number of structure? Will it be the government's mandates, the regulation? What will it be? So for our product development view is always, when we design a product, put in a new technology, it's always how and what the customers think, want, and desire. So that we put into our map and draw it and to realize into the product. And another is we put this kind of technology, what's the vision to achieve, to contribute, and also to change. That will be the challenge for us. Okay, so it's all my presentation. I hope it's more much the academic part, but I hope my industry experience can give you a reference for the future. If we want to link the technology into products, you can have some thinking for it. Thank you very much.
Thank you very much, Dr. Law. I think your presentation is very exciting, and I really like the video, which is the first time for me to watch that as well. It really gives a clear picture why V2X is needed. And I think we have two questions. The first question is regarding to that topic. Has V2X been deployed on all new Toyota vehicles globally? And will different markets have different deployment strategies? Say Japan, China, and US, and maybe Europe, do they have different strategy?
Yes, now currently the products only provided in Japan. And also before we evaluate to provide in US, but because of the frequency issues, we postponed, and we are also looking for the next direction. We think if FCC settle down and like Ford, GM start to launch new V2X vehicle, we Toyota will follow it. And for China, we know they are already starting to have some OEMs start to ship in the V2X vehicle, and we are still looking closely to it. and we will provide the vehicles when the products, if the market is already started. And one thing is the structure is normally we follow the local governments because we know there are frequency standards. We follow those kind of things so that if US decides, okay, CV2X or DSRC, then we will just follow it and provide the product. If China they decide to use CV2X, then according to China market, we will provide CV2 products. It's like that.
Okay, understood. Thank you. And the second question is, how hard is the effort to work with the government to deploy this kind of ITS Connect technology? And he assumes this cannot be done by a single OEM, and it must require collaborations across multiple stakeholders. How hard is it?
Yeah, it's actually the ITS Connect. We are talking with the Japanese government. Japanese government is funding all those kind of things, and they are trying to put the infrastructure and making some standardization bodies to make the B2S realize. And also we collaborate with other OEMs. Actually, we have in the, I think, several years, the ITS World Congress, we have tested Toyota with other OEMs, interconnectivity of V2X. We have demonstrated, but still some OEMs still have some concern because of the V2X. Some OEMs prefer this wait until the global markets to start, then they start to provide the V2X. So each one has its own concerns. And in Japan now, the infrastructure is still we think the bottleneck because the numbers still few. So we still continue to talk about to the government to increase the ITS infrastructure. But of course, we need to see, just now we talk about the wins. ITS always have big challenges. There's no clear business model for it, so that it's hard to get return, so how to get maintained. So how to make the scheme for the government and also for the OEMs and also other industry, I would think will be important, such as how to use the V2X data effectively and to improve maybe other business, to get other business to involve. We think is also important. Yeah.
Okay, thank you. Thank you very much, Dr. Law, for your presentation. Yeah.
Thank you.
Yeah, let's move on to our last but not least presenter, Dr. Xuesong Zhou. And,
okay.
Yeah, Professor Zhou. Yeah, Professor Xuesong Zhou joined the School of Sustainable Engineering and the Built Environment at Arizona State University in 2013. Previously, he was an associate professor at University of Utah. He has been assisting the Federal Highway Administration to develop and provide technical support for large-scale simulation-based dynamic traffic assignment system for the past 10 years. He serves as an associate editor for Transportation Research Part C, Emerging Technologies, and his research work focuses on dynamic traffic assignment, traffic estimation prediction, large-scale routing, and rail scheduling. Professor Zhou, please go ahead.
Yeah, thank you, Dr. Wang. Thank you for the audience today. I try to present my slides within 20 minutes.
We have time, Professor Zhou.
Okay.
We have time all the way until 7. So.
Okay, thank you. So the topic is about the CV modeling with a digital twin. And my main motivation is try to make more friends, try to make sure you can connect it to our modern community in transportation planning and system optimization. Our goal is try to make sure we understand the availability of the open data, open standard in the network modeling domain, and also how we apply the different methodology and the challenges we see from both researchers and the city planners. Currently, I have a lot of open source development along this line. So if you are interested, you can always visit our ASU Transportation plus AI Lab in the GitHub. Going back to the evolution of the digital twin, we know starting from 1960s, we have a computer-driven simulation, and then around 2000, they have the simulation-based system design. So starting from the NASA white paper on digital twin in 2011. At the current stage, there are many digital twin prototype. And what we want to provide to you is not just about the advertisement, how great or how interesting the digital twin could be. I try to show you our motivation, how we can create the digital twin quickly, and how we can use the open specification to collaborate. And later we will present 2 research tracks we have. One is high fidelity CAV simulation. Another is how we can bridge the gap from the large scale planning to the high fidelity simulation. I have these 4 motivating questions to ask. First of all is there's many companies are building their own version of the digital twin for different smart city applications. But how we can encourage the collaboration between OEMs, researchers, planners, and engineers in the field. Second one is, as our research community have been using different open source, open tools, how we can join effort together, try to pave the way for some interesting application and the real world deployment. We will try to show our experience, our recent experience of developing a high fidelity multimodal simulator. The last question actually is the most theoretically important question. Can we bridge the gap between multi-resolution modeling? Because in the traffic flow theory, we know you can use a micro simulation model to derive these speed density aggregated relationship, and also you can have another way around. We should use these kind of theoretical results to show more insights and to guide our simulation. Therefore, my research topic today will be presented in 4 different small parts. The first part is to show our experience of using open data specification and different open source tools around this line. Second one is our quick demonstration of this CAV Lite is an open source high fidelity simulator still in the progress. Number 3 is try to show our perspective in internally consistent multi-resolution model for the larger scale systems. And the last one is we try to enable some quick decision support along this line. So let's back to the first topic. The digital twin, or all these fantastic CAV modeling, is interesting research area. But we do see at the current stage, at least in my transportation planning area, we have many different parts. We have a sensor data, planning model, traffic simulation model, dynamic traffic assignment model. Over the years, we need to make sure the product or the models we develop can apply at the largest scale system and can be linked to the data intensive system, and also should maintain internal consistency in both modeling and data representation. So starting 2010, actually, my team has been developing the DTA Lite as a microscopic open source traffic simulator. We have many wonderful applications, but we recognize that there's still a lot of challenges. In particular, when we try to connect our system into different either simulation system or into highway capacity estimate into the sensor, such as the speed or density measurements. I want to make our audience aware of this recent effort by Federal Highway, GAMS. This is the joint effort, very similar to GTFS, which is a Google Transit Feed. The objective of this specification is to provide a common human machine readable format to share all the routable network. I have a long list of all the participating agencies and planners and also different companies. So you can see PTV and Cube, Enroll, they are all in this group. Currently, I think many transportation simulation companies will slowly, but will eventually make their network model coded into this open standard. So by using this open standard, we hope starting from this network representation, we can have a systematic coupling between different elements. Otherwise, we only see on the left is what ad hoc connection, and on the right we see it is a much more consistent representation to facilitate the good transportation application. So let me try to demonstrate a number of open source tools. You can always feel free to download those tools from the Python website or to look at our source code. OpenStreetMap is an open source database available free for any city, any region. So my student Jay, I believe he's also in the audience, developed together with me this OSM to GAMS. OSM is an OpenStreetMap. GAMS is a data standard we just mentioned. So we add many nice functionalities, consolidate intersection to deal with missing data, to add the point of interest into the planning network. A recent practice we have is we can show, using our open source package, you can explore the whole United States regional, I will say the state nationwide network with 10,000 nodes, 10 million nodes, okay, 10 million nodes. And if you try to have a high fidelity representation cell to cell, you will use our package, and you can have a much larger and high fidelity representation along this way. The package is quite stable. We receive more than 20,000 downloads at this point. Second package is grid to demand. So we recognize a need to create the different OD demands. So we use the traditional 4-step process, but we use the grid cell to create this production attraction, try to allow the planners or allow researchers to create the demand quickly. And these two can be applied at a different scale of the system. Signal, by working with Milan, who is also a assistant professor at the University of Wyoming. Previously, I worked with him together at the University of Utah. We create two versions. One is an Excel version of the Sigma X. The other is a volume to timing and a Python API for you to incorporate synchro data or create this default signal timing for any intersection using the GMS data standard. If you want to calculate the shortest path, Dr. Pei-Heng Lee, who is our ASU graduate in 2017, created this Python package to calculate the end-to-end shortest path using this data standard. We also have other friends in our community, such as one of very popular AB3 simulator developed by Dustin in Seattle, and he's using our volume to timing to generate the default signal timing in order to really allow the large scale, quick deployment of his traffic simulator. So in long term, we hope we can integrate network, demand, supply, and a simulation component. And we hope this community can be built on this open data network representation. The idea is we try to get this network quickly, and then later we can establish a very consistent multi-resolution modeling. So this goes to my second topic of the day, how we try to show we have a CAV light as an open source tool to build those network and to allow some easy representation for your research. So we do know Sumo is one of the leading open source package in the field. They are using space continuous and time discrete vehicle movement. They can model many high fidelity vehicle interaction, and I think they have a wonderful community at the current stage. So what we see is the challenge for us is how we can incorporate the distributed control framework, how we can add the different optimization components, how we can ensure the consistency between the high fidelity, low level representation to a regional level application. So by recognizing these challenges, our student Jay, who developed the OSM to GMS, we have a package, CAV Lite. We try to recognize those motivation and try to provide bi-level hybrid, integrated simulation, control, and optimization package. All motivation are coming from this virtual track modeling framework, starting from NSF project. As you know that the safety on the railway system is extremely high because they have the different moving block, either manual block, automated block, and the moving block to incorporate the state-of-the-art communication into their safety guarantee driving maneuver. So along this line, the motivation for us is we split a long link or a segment into different small cells or blocks, and then we will allow the users to model the lane changing, model the merge, diverge behavior in a much more systematic way. So as you can see on the left, we have the physical road system. On the right, we are building this cyber track system because as we know that we are now using the physical track as a railway system, we digitize those small segments in the digital twin, quote unquote, representation to model car falling, lane changing, emergency response, leading, and the platoon evaluation. So as you can see, at the current stage, we do have an integrated simulation and optimization framework, and we have two levels, macro level, link by link, intersection wise, and the micro level, which we use 7 meter or 5 meter, depending on your definition, to create a lane by lane simulation representation. So as you can see, we present these two layers of the network. And if you zoom into one particular intersection, once you have the OpenStreetMap, we have a tool which is called net to cell, help you to generate these default lane by lane, lane changing simulation network, for you to conduct your own research. We do demonstrate that if you try to model the lane changing or model these route choice, you can develop a consistent route choice model based on the cells. This route choice model is represented in 3 terms: estimated cost to the end of the destination, waiting cost, and the moving cost. I don't want to enumerate in all the details here. This is a quite open framework for you to consider both lane changing and the car falling in a very consistent way. The traffic signal control was provided from the meso layer, movement layer, back to this cell layer. So in this case, you can very efficiently model this movement layer signal timing to the cell-based traffic movement control. I do have a representation here, try to show our animated, vehicle trajectory. We can use both 2-dimensional view and a 3-dimensional view to investigate, all the safety and efficiency along this way. So typically, the CAV light is executed in this following workflow: prepare the data, OD estimation, calibration of the route choice, simulation using our CAV light, and then do the visualization. So in particular, the network representation was created by the net to cell. We can create the lane by lane, movement by movement, and even the lane changing arcs, all through this package based on any city in the OpenStreetMap from the beginning. So by doing so, we hope we can allow the researchers to look at the safety, to look at the cell-based link flow, and to look at other driving behavior along this line. So for simplicity, you can try to look at how the CAV, human-driven cars, are merged. So if you use the grid-based, the cell-based representation, the question could be quite interesting. where are the merging points? Where are the likely merging points depending on the geometry of this merging section? What are the likelihood of the lane changing before in the intersection? And what are the lane changing time duration? So by doing so, we hope with a gray-based, fully discretized network will help you to capture many behavior factor into this representation. So we have been using our space-time network to represent this system as optimization. So you can see for each node, I and J, we have the different time dimension. We have traveling arc, we have waiting arc. So we want to show that the signal control can be very easily integrated into this system. Once signal light turns to red and the corresponding space and time arc will be removed or will be disabled in our representation. So for simplicity, I just list this discrete time network optimization model on the left, try to show you that we are using the newest simplified car-forming model to literally simulate the trajectory into this space. And we are welcome other researchers to look at this discretized network with your continuous optimization, which has been mentioned in our previous talk. If we only consider this as an integer programming optimization problem, simply using the integer programming solver will be very difficult. So we only report some statistics, and we do develop some TensorFlow computation graph-oriented optimization framework along this line. We just want to say this network opens the door, for us to look at the corresponding optimization for the trajectory. So my last research topic is about how we can maintain the consistency. We like to do this trajectory optimization, but on the other hand, we know in traffic flow theory, all the car-following models can be integrated into the steady state average speed density relationship. And in order to provide the digital twin decision support, we still need to aggregate those relationship into the speed density relationship. And we know from the early presentation, there's many different fundamental diagrams. Professor D from University of Columbia already mentioned there's a couple of fundamental diagrams in her calibration framework. If you look at the existing fundamental diagram, there are a lot of challenges. Some of them have 2 parameters, difficult to capture the whole traffic dynamics. 5 parameters will be too much for us to calibrate all the details. So we just want to show you that recently, this is a paper to be published in Transportation Research Part B with a collaboration with Professor Liu from Southeast University. We developed a S3 model with the 3 parameters with S-shaped traffic stream model. The first author, Kevin Chen, currently is a postdoc at the university in Hong Kong. So we use these 3 parameters to show that with the 3 parameters, free flow speed, critical density, and the aim as a maximum flow inertial coefficient, you can try to describe the different traffic behavior in Germany, in India, in China, in the United States, or maybe in a very high efficient driving condition in Japan. So by using these 3 parameters, we are able to capture the inertia for the different driving population in terms of maintaining the maximal efficiency in the system. And in this recent work, we are able to show that using these 3 parameters, we can capture the capacity constraint, we can capture how the capacity will be controlled under the different critical density. And also we show there's a consistent relationship between our speed density relationship and with another GM like General Motors based car-following model. So we calibrate our model using the Loop 101 or US11 dataset in California. We also use NGSync to calibrate our model. What we try to report back to you here is this parsimonious model is able to capture the both speed and the flow relationship, and compared to the existing models, our model, if you look at the last two columns, we are one of the top performers in this case. We are currently also working on the congestion duration calibration for Washington, D.C. area, and they asked us to use the different representation to capture the congestion duration from 9 to 10, capture the most congestion point along the corridor. So we are working on them along this line, try to really build a much more consistent relationship from the MISO relationship of the queue to the macro relationship of the total demand and the queued demand. So many planners, they know we have been using the volume delay function for a long time, and we are helping the planners in the different regions to calibrate this model. We are not just calibrate the traditional BPR function. We say they need to have this queue demand perspective starting from the fundamental diagram, so that we can use some closed form solution to manage the overall congestion duration at a different corridor scale first, and then later we can control from the lane capacity to the driving headway to the detailed driving trajectory. So that is the multi-resolution perspective we try to offer today. Finally, we are currently working on this Washington, D.C. dynamic traffic assignment deployment together with Northern Virginia Transportation Authority. And this decision tool eventually will help them to make the programming decision, and this decision tool will help them to allocate the funding for the next six years. And this is our motivation, try to build this digital twin for informed decision support. Finally, this is my slide. At the ASU, we are working closely with the different community, with the different planners. We hope by using this open standard, by highlight the need for this network-wide high fidelity simulation platform, and also by highlight the need for the theoretical consistent traffic flow model along this line, we hope we can try to work with different communities and streamline the process and transform this research into the practice. This is the end of my presentation. Thank you.
Thank you very much, Professor Zhou. I think we have a few questions, and I can ask on behalf of the audience. The first question is, how do you update the database of digital twins? Is there any like incremental learning element in there, or every time the whole database has to be updated, which could be time and computation inefficient?
This is a good question. So at the current stage, we are still mostly offline at the offline setting. In the online setting, we need to solve these traffic estimation, traffic prediction problem first. My talk are still mainly focused on the network and some preliminary database, and we have not going to this edge computing domain yet.
Okay, understood. And maybe the second question is somewhat related. And he is curious on how does the digital twin help model the traffic estimation and prediction? Is it a data-driven method, or is it more like a framework?
So I think we have very similar methodology as Professor B. We are having a computational graph-based TensorFlow implemented consistent representation. So we are not think the machine learning just as a machine learning. We think the machine learning offers this computational framework for nonlinear optimization, nonlinear control. So another research direction working with Dr. Rampaniala at the ASU, we prove that using the machine learning, we can calibrate the discrete choice model, network optimization model. We can achieve much more consistent and also online computational framework. So this is related to the computational graph oriented representation in my another research track.
Okay, thank you. And the third question is how to integrate CAV-induced demands modeling in your framework. How to integrate CAV-induced demands modeling in your framework.
Yeah, this is also, thank you, Guang Yuan. Yeah, this is related to the joint research with Dr. Rampandiala. And we do calibrate the root choice model, and we try to make sure we model the CAV-induced demand in a consistent way, which means when there's a more induced demand in this area, traffic congestion might be increased, and then the induced demand will, look at their behavior again and then to retrieve the final consistency result. So I think the question is very interesting, but the answer is quite complicated. How you can ensure when we model induced demand, we can make sure they are converged to a steady state, and other than just simply assume 20% or 10% induced demand.
Okay, got it. Thank you. Thank you one more time, Professor Zhou, for this presentation and to join us as well. Thank you.
Okay, thank you for the opportunity, and you please feel free to contact me or contact GMS Data Framework at the University of at the different universities here, because we have, it's not just ASU, and also contact the Federal Highway and the WOPI Research Center. They are more than happy to work with different modelers into this new open platform. Thank you.
Thank you, Professor Zhou. And I think this concludes this workshop. And let me quickly share this one more time of our organizers. I want to thank all those workshop organizers of this particular workshop, Professor Qi Zhu from Northwestern University, Dr. Guoyun Wu from UC Riverside, Professor Jiaqi Ma from UCLA, Professor Changwei Lin from National Taiwan University, and Dr. Bowen Zheng from Pony.ai. And Professor Zhu, I'm not sure whether you can speak a few words here.
Sure, I'll be glad to. I really want to first I will thank everybody for coming right on Sunday afternoon with all the NFL games and Emmy Awards going on. But I stay for the whole session. Honestly, I feel like this is much more exciting. The discussions cover such a wide range, right, from all the way to human-machine interaction to the grand vision of vehicle computing to some of the very fundamental technical techniques on safety, security, combination of physical-based model and data-driven methods, to the I think practical application of V2X, and then to the introduction of such a variety of different simulation tools. I hope this will be beneficial to everybody who have attended. And finally, I really want to thank Ziran to do all the heavy lifting to put together a program. This is really wonderful. Thank you so much, Ziran.
Yeah, thank you, Professor Zhu, and thank you everyone for attending. We will be sending out the announcement next week regarding, of course, this video recording of this workshop, along with a few other resources like some special issues and also the open data set Professor Zhou just talked about. So let's keep in touch, and thank you again for attending this workshop. Thank you.
Thank you. Bye.
Bye. Thank you. Bye.